Tonight, we're going to explore one of the most fundamental aspects of reality: gravity. You experience it every single moment of your life. It keeps your feet firmly on the ground. It keeps the atmosphere wrapped protectively around Earth. It keeps Earth orbiting the Sun in a dance that has continued for over 4.5 billion years. It governs the motion of galaxies billions of light years away, holding together structures so vast they defy human comprehension. And here's the twist that's going to fundamentally change how you see the universe, how you understand your place in it, and how you think about motion itself. Gravity isn't actually a force at all. It's something far stranger, far more elegant, and far more beautiful than that. Understanding what you think you know about gravity. Consider what you think you know about gravity. You drop an object and it falls down. Simple, right? You've been told since childhood that Earth's gravity pulls things toward the ground. That gravity is a force pulling you downward, keeping you anchored to the planet's surface. That the Sun's gravity pulls Earth into orbit around it, keeping us from flying off into the cold darkness of interstellar space. Most people believe exactly that. Schools teach exactly that. And while it's not exactly wrong, it's woefully incomplete. It's like saying the Earth is flat because it looks flat when you're standing on it. It works for everyday purposes, allows you to navigate your immediate surroundings, but it misses the deeper, more profound truth lying beneath the surface appearance. Isaac Newton figured out the mathematics of gravity in 1687 when he published his book, Mathematical Principles of Natural Philosophy, usually just called the Principia. One of the most important scientific works ever written, a book that transformed human understanding of the physical world. Before Newton, ideas about why things fell or why planets moved were mostly philosophical guesses, speculation without mathematical foundation. People believed that earthly objects and celestial bodies operated under completely different sets of rules, that the heavens were governed by divine principles fundamentally distinct from the physics of the mundane world. Newton changed everything with a single revolutionary insight. He showed that the same force that makes an apple fall from a tree also keeps the moon orbiting Earth and Earth orbiting the sun. Revolutionary doesn't even begin to capture the magnitude of this realization. Because people thought the heavens and earth operated under completely different rules, governed by different gods, different principles, different laws. Newton unified them with one elegant set of mathematical laws, showing that the entire universe operates according to the same fundamental principles, whether you're on Earth's surface or drifting through the depths of space. Newton's law of universal gravitation. Newton's law of universal gravitation states that every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between. Let me break that down into understandable pieces. Earth and you pull on each other hard because Earth is massive, containing approximately 5.97 times 10 to the 24th kilograms of matter. You and a pencil across the room also pull on each other gravitationally, but so weakly you'd never notice it in a million years of observation. Exactly how weak are we talking about? If you tried to build a gravitational wave-style detector sensitive enough to register a single person walking past the laboratory, the two arms of the interferometer would need to be roughly the distance from our star to Saturn, approximately 10 billion kilometers or 6 billion miles long. Anything shorter, and the signal would be completely swamped by quantum and thermal noise, drowning in the background chaos of the universe. That's why you can feel the tiniest magnet pulling on a paperclip or a static shock from a doorknob after walking across a carpet. Yet two people standing a meter apart attract each other gravitationally by less than the weight of a single bacterium. Gravity is 39 orders of magnitude weaker than the electromagnetic force on everyday scales. One of the deepest unsolved mysteries in physics, a puzzle that has haunted theorists for generations. And that's before we even get to the inverse square law, one of the most important mathematical relationships in all of physics. Double the distance between two objects, and the gravitational pull doesn't just halve, it drops to a quarter of its original strength. Triple the distance, and it falls to 1/9. That's what makes gravity dominate only when the masses get truly enormous, when you're dealing with planets, stars, and galaxies rather than everyday objects. Newton's equations worked beautifully for over 2 centuries. They could predict the motion of planets with incredible accuracy, allowing astronomers to forecast eclipses decades in advance. They explained tides, the ocean rising and falling in predictable patterns because of the moon's gravity pulling on the water, creating bulges that move around the planet as Earth rotates. They explained why planets farther from our star move slower in their orbits, a relationship discovered by Johannes Kepler but explained by Newton. They allowed scientists to discover new planets by observing tiny irregularities in the orbits of known planets, using mathematics to predict what couldn't yet be seen. That's how Neptune was discovered, a triumph of mathematical physics. In 1846, astronomers noticed that Uranus wasn't moving exactly as Newton's equations predicted. The deviations were small but measurable and consistent. They calculated where an unknown planet would need to be to cause those deviations, applying Newton's laws backwards to infer the existence of something invisible. They pointed their telescopes at that spot in the sky, and there was Neptune, right where the math said it should be. A world never before seen by human eyes, but predicted purely through mathematical reasoning. For over 200 years, Newton's laws were considered the final word on gravity, the ultimate truth about how the universe operated, the problem that wouldn't go away. But there were small problems, tiny cracks in the edifice that refused to be explained away. The most famous was Mercury's orbit, a puzzle that nagged at astronomers for decades. Mercury orbits the Sun in an ellipse that slowly rotates over time, a phenomenon called precession. Newton's equations predicted how much Mercury should precess based on the gravitational influences of other planets, particularly massive Jupiter pulling on Mercury's orbit. But the observations didn't match the predictions. Mercury was precessing roughly 43 arcseconds more than predicted per century. That's approximately 1/180th of a degree per century. Incredibly small, almost negligible, but real and measurable and completely unexplained by Newtonian physics. Scientists searched desperately for explanations that would preserve Newton's laws. Maybe an undiscovered planet called Vulcan, orbiting even closer to the Sun than Mercury, was pulling on Mercury's orbit. Astronomers searched for Vulcan for decades. It didn't exist, a ghost planet that haunted 19th century astronomy. Maybe Newton's laws needed slight adjustment, a minor correction term. Nothing worked. The discrepancy remained, a thorn in the side of physics. The mystery remained stubbornly unsolved until 1915, when Albert Einstein published his general theory of relativity, a work that would revolutionize our understanding of space, time, and gravity itself. Einstein's radical insight. Einstein's insight was radical, so profound that it took years for the scientific community to fully appreciate its implications. Gravity isn't a force at all. Rather, it's a curvature of space-time itself. That probably sounds like meaningless word salad at first hearing. Curvature of space-time. What does that even mean? How can space and time curve? Let me explain it step by step, building up from concepts you already understand, constructing a bridge from everyday experience to this strange new reality. First, consider space and time separately, the way we normally think about them in our daily lives. Space is the three-dimensional arena where things exist and move. You can move forward and backward, left and right, up and down. Those are your 3 dimensions of space, the coordinates that define every position in the physical world. Time is different from space in our everyday experience. It flows in one direction from past to future. You experience events in a sequence, one after another. You can't move backward in time or jump forward arbitrarily, skipping over the intervening moments. Space and time seem fundamentally different in character and behavior. Space is where things happen. Time is when they happen. 2 separate stages for the universe's drama to unfold. But Einstein showed that space and time are not separate entities at all. They're woven together into a single four-dimensional fabric called spacetime. Not just a mathematical trick for simplifying equations, but a description of physical reality, of how the universe actually is at its most fundamental level. You can't have space without time, or time without space. They're aspects of the same thing, as inseparable as the height and width of a surface. When you move through space, you also move through time. When time passes for you, you're also moving through space-time, even if you're sitting perfectly still in space. Even if you're sitting still relative to Earth's surface, you're moving through time. And that movement through time is movement through space-time. Every event in the universe happens at a specific location in space-time. Not just a position in space and a moment in time considered separately, but a unified point in four-dimensional space-time. Your birth happened at a specific point in space-time. Reading these words is happening at a different point in space-time. Space-time is a unified four-dimensional structure, and understanding this is crucial to understanding gravity, the fabric of space-time. Here's where it gets truly interesting, where the real magic begins. Space-time is not rigid like a stage set. It's flexible, dynamic, responsive. It can bend and curve and warp. And what causes it to curve? Mass and energy, the fundamental constituents of the physical universe. Any object with mass or energy curves the space-time around it, creating what we might think of as dips or depressions in the fabric of reality. The more massive the object, the more dramatically it curves space-time in its vicinity. Earth curves space-time around it, creating the gravitational field we experience. Our star curves space-time much more because it's much more massive, containing 99.86% of all the mass in the solar system. Even you curve space-time a tiny amount, an infinitesimal distortion that's real but unmeasurable with any current technology. Everything with mass or energy curves space-time to some degree. There's no object so small that it doesn't affect the geometry of the universe. Think of space-time like a stretched rubber sheet, a trampoline pulled tight. If you place a bowling ball on the sheet, it creates a dip or depression, a visible curvature in the previously flat surface. The heavier the ball, the deeper the dip it creates. If you roll a marble near the bowling ball, the marble doesn't travel in a straight line across the sheet. It curves toward the bowling ball, following the slope of the depression created by the bowling ball's weight. From the marble's perspective, assuming it's conscious, it's just following the straightest path available through the curved surface. But because the sheet is curved, deformed by the bowling ball's presence, that path curves toward the bowling ball. The marble isn't being pulled by a mysterious force. It's simply following the geometry of the curved surface. Similarly, in the real universe, Earth curves space-time around it like the bowling ball curves the rubber sheet. When you drop a ball, the ball isn't being pulled by an invisible force, reaching out and grabbing it. It's following the straightest possible path through curved space-time, a path we call a geodesic. That path happens to curve toward Earth's center because Earth's mass has curved space-time in that region. The ball is simply doing what comes naturally, following the geometry, the limitations of analogies. Now, the analogy has significant limitations, and we need to be honest about them. The rubber sheet is a two-dimensional surface being bent in a third spatial dimension that we can see. But space-time is four-dimensional, 3 dimensions of space plus 1 of time, and it's not bending into some higher dimension that we could point to or visualize. It's intrinsically curved, meaning the curvature is a property of space-time itself, built into its geometry, not a bending into something else outside it. There's no outside. The universe is space-time, and space-time is the universe. Also in the rubber sheet analogy, we're using gravity itself to make the ball sink into the sheet, to create the depression. That's circular reasoning when we're trying to explain what gravity actually is. We're using gravity to explain gravity. So the analogy is useful for initial visualization, for getting a feel for the concept, but don't take it too literally. Don't imagine that there's actually a rubber sheet somewhere that reality is written on. It's a metaphor, a teaching tool, not the thing itself. What curved space-time really means. What does it actually mean for spacetime to be curved in a precise, mathematical sense? The rules of geometry are different in curved space than in flat space. In flat space, the kind described by Euclidean geometry you learned in school, the shortest distance between 2 points is a straight line. But in curved space, straight lines don't exist in the usual sense. Instead, there are geodesics, the paths that represent the shortest distance between 2 points in that curved space, the straightest possible paths given the curvature. On Earth's surface, which is curved, forming roughly a sphere, the shortest path between two cities isn't a straight line through the air if you could tunnel through the planet. If you had to stay on the surface, constrained to move along the curved surface of Earth, the shortest route is a curve following what's called a Great Circle route. That's why flights from New York to Tokyo fly over Alaska, a route that looks completely bizarre, almost nonsensical, on a flat map. It looks like the plane is going thousands of miles out of the way. But on a globe, when you account for Earth's actual curvature, it's actually the shortest route possible while staying at constant altitude above the surface. The path that minimizes distance and therefore fuel consumption and travel time. In curved spacetime, objects follow geodesics, the spacetime equivalent of straight lines. A planet orbiting our star isn't being pulled by a force emanating from the sun. It's following a geodesic through the curved spacetime created by the stellar mass. From the planet's perspective, it's moving in a straight line through spacetime. It's not turning, not accelerating in its own reference frame. But because spacetime is curved by the sun's mass, that straight line through spacetime from our external perspective looks like an orbit through space. The planet is constantly falling toward our star, following the curvature of spacetime, but also moving sideways fast enough through space that it keeps missing the sun, maintaining a perpetual state of freefall that we call an orbit. Why astronauts float. This elegant explanation reveals why astronauts in orbit around Earth experience weightlessness, floating inside their spacecraft as if gravity had simply turned off. They're not beyond Earth's gravity, not even close to escaping its influence. The gravitational field at the altitude of the International Space Station, which orbits roughly 400 kilometers or approximately 250 miles above Earth's surface, is still around 90% as strong as it is on the ground. The difference in gravitational pull between the surface and the ISS altitude is relatively small, only about 10%. The astronauts feel weightless, floating freely inside the station, not because there's no gravity affecting them, but because they're in freefall. They're following a geodesic through curved spacetime without anything pushing on them. Earth curves spacetime and the space station follows that curvature, constantly falling toward Earth but moving sideways fast enough through space to keep missing it, tracing an elliptical path around the planet. The astronauts inside are falling at exactly the same rate as the station itself. So relative to the station, they're weightless, floating as if gravity didn't exist. When you stand on Earth's surface, you're not following a geodesic freely through spacetime. The ground is pushing up on you, preventing you from following that natural freefall path. That push from the ground is what you feel as weight, the sensation of gravity pulling down on you. The ground is accelerating you away from the geodesic path you would naturally follow. And that acceleration is what creates the sensation you interpret as weight. In a very real sense, standing still on Earth's surface means you're constantly accelerating upward through space-time, being pushed away from the natural geodesic by the electromagnetic forces of atoms in the ground resisting compression. Einstein's field equations. Einstein's field equations describe exactly how mass and energy curve space-time, and how that curvature tells objects how to move. The equations are fiendishly complex, among the most difficult in all of physics. They're a set of 10 coupled, non-linear partial differential equations, meaning they're interconnected in ways that make finding solutions extraordinarily challenging, even with modern supercomputers. Each equation describes a different component of spacetime curvature, and they all influence each other in complicated ways. Solving Einstein's equations for realistic situations, like a collapsing star or two black holes, spiraling together, often requires massive computational resources. Supercomputers running for weeks or months to simulate just seconds of physical time. The mathematics is brutally difficult, pushing the boundaries of what even the most powerful computers can handle. But when scientists solve them, the equations make predictions that differ slightly from Newton's laws in extreme situations. In regions where gravity is particularly strong, or objects are moving at significant fractions of light speed. The Mercury problem solved. Remember Mercury's orbit, the anomalous precession that had puzzled astronomers for decades. When Einstein applied his new equations to Mercury's motion, accounting for the curvature of space-time near our massive star, the equations predicted exactly the 43 arcseconds per century of extra precession that observations showed. Exactly. With no adjustable parameters, no fudge factors, no mysterious, undiscovered planets required. The math simply matched reality perfectly. Einstein later said that when he realized this, his heart began to palpitate wildly, that he was beside himself with joy and excitement. For days, he couldn't work on anything else, couldn't think about anything else, because he knew with absolute certainty that he'd discovered something profoundly true about the universe. That was the first experimental confirmation of general relativity, a triumph that came from the theory's own internal logic rather than from a specially designed experiment. But there were more dramatic predictions to come, phenomena so bizarre that even Einstein sometimes doubted they could be real. Gravitational lensing and bending light. General relativity predicts that light itself should follow curved paths through warped spacetime. Photons have no mass, zero rest mass according to all measurements, but they do have energy. And Einstein's famous equation, energy equals mass times the speed of light squared, showed that energy and mass are interchangeable, two forms of the same fundamental quantity. So energy also curves space-time and is affected by space-time curvature. Light, passing near a massive object, should have its path bent by the curvature of space-time around that object, deflecting from the straight line it would follow through flat space. In 1919, just 4 years after Einstein published his theory, British astronomer Arthur Eddington led an expedition to observe a total solar eclipse. During the eclipse, when our star's light was blocked by the moon, stars near the sun's edge in the sky became visible, their faint light no longer drowned out by the sun's brilliance. Eddington measured the positions of those stars and compared them to their known positions when the sun wasn't nearby in the sky, positions measured months earlier when Earth's night side faced that region of space. The stars appeared shifted from their true positions, displaced outward from the sun's edge by approximately 1.75 arcseconds, exactly as Einstein's equations predicted. The starlight had been bent by the sun's gravitational field, by the curvature of space-time around our star, causing the stars to appear in slightly different positions than they actually occupied in space. When the results were announced, Einstein became an overnight celebrity, catapulted to worldwide fame. Newspapers around the world trumpeted the confirmation of relativity. Newton's laws, which had reigned supreme for over 2 centuries, had been superseded by a more accurate theory. This gravitational lensing effect has become a powerful tool in modern astronomy. When light from a distant galaxy passes near a massive object like a galaxy cluster or an individual galaxy positioned between us and the distant galaxy, the intervening mass curves spacetime enough to bend the light significantly. Sometimes, the bending creates multiple images of the same background galaxy spread around the lensing mass like jewels on a necklace. Sometimes it stretches the background galaxy into arcs or rings, beautiful curved streaks of light wrapped around the lens. By studying these distortions carefully, measuring how much the light is bent and in what patterns, astronomers can map out how mass is distributed in the lensing object, including dark matter that emits no light but still curves spacetime through its gravitational influence, time dilation, and the GPS system. Another prediction of general relativity is gravitational time dilation, one of its strangest and most counterintuitive consequences. Time runs slower in stronger gravitational fields, in regions of more curved spacetime, not just appears to run slower from some external perspective, but actually runs slower in an absolute, measurable sense. A clock on Earth's surface, deep in Earth's gravitational well, ticks slower than an identical clock orbiting high above Earth, where spacetime is less curved by Earth's mass. The effect is tiny for everyday purposes on Earth. Clocks on the ground run slower than clocks at high altitude by roughly 1 part in 10 to the 16th per meter of height difference. That means for every meter you climb up a mountain, your clock gains about 100 femtoseconds per day relative to a clock at sea level. A femtosecond is 1/400,000th of a second, an unimaginably tiny interval. You'd never notice this in everyday life, would never experience time passing differently when you climb stairs or take an elevator to a high floor. But the effect matters enormously for the global positioning system, for GPS satellites that provide the navigation data your phone and car use every day. GPS satellites orbit at an altitude of roughly 20,000 kilometers, or about 12,400 miles above Earth's surface. At that altitude, gravitational time dilation causes the satellite clocks to run faster than clocks on the ground by about 45 microseconds per day. 45 millionths of a second per day, which sounds small but is huge for precision timing. GPS works by having satellites broadcast precise timestamps synchronized to atomic clocks on board. Your GPS receiver picks up signals from multiple satellites and calculates your position based on the tiny differences in arrival time of those signals, triangulating your location. Light travels at roughly 300,000 kilometers per second, or about 186,000 miles per second. In 45 microseconds, light travels roughly 13.5 kilometers, or about 8.5 miles. If GPS didn't account for gravitational time dilation, if the system didn't constantly correct the satellite clocks for relativistic effects, your position calculations would drift by more than 10 kilometers per day, making the system completely useless for navigation within days. There's actually another relativistic effect that also matters for GPS. Special relativity, Einstein's earlier theory about objects moving at constant high speeds, predicts that moving clocks run slower than stationary clocks. The GPS satellites are moving at roughly 3.9 kilometers per second, or about 2.4 miles per second relative to Earth's surface. That motion causes their clocks to run slower by about 7 microseconds per day. Combining both effects, general relativity's gravitational time dilation makes the clocks run faster by 45 microseconds per day, while special relativity's velocity, time dilation, makes them run slower by 7 microseconds per day, for a net effect of roughly 38 microseconds per day faster than ground clocks. The GPS system accounts for both effects, adjusting the satellite clock rates so that they stay synchronized with ground clocks despite the relativistic effects. Every time you use GPS to navigate to a destination, you're relying on Einstein's theories of relativity, confirming their predictions billions of times per day around the world. Relativity isn't just abstract theory confined to physics textbooks and research papers. It's technology you depend on, built into the infrastructure of modern civilization. Black holes and extreme space-time curvature. General relativity predicts one of the most extreme and fascinating objects in the universe, black holes. When you compress enough mass into a small enough volume, creating sufficient density, the space-time curvature becomes so extreme that nothing can escape, not even light itself, the fastest thing in the universe. The boundary around a black hole is called the event horizon, the point of no return. If you cross the event horizon, all possible futures lead inward toward the singularity at the center. There's no escape, no trajectory that leads back out, no amount of thrust or speed that can overcome the space-time geometry. And we're not talking about a force pulling you in that you might resist with a powerful enough rocket. We're talking about the geometry of space-time itself, the very structure of reality, being so warped that all paths forward in time lead toward the center. Trying to escape from inside the event horizon would be as futile as trying to travel backward in time, attempting to alter the fundamental arrow of temporal progression. The size of the event horizon depends on the black hole's mass through a quantity called the Schwarzschild radius. For a non-rotating, spherically symmetric black hole, the simplest case, the Schwarzschild radius equals 2 times the gravitational constant times the mass divided by the speed of light squared. For an object with Earth's mass, that's roughly 9 millimeters, or about 1/3 of an inch. If you could somehow compress all of Earth's mass into a sphere 9 millimeters across, smaller than a marble, it would collapse into a black hole. For our star, the Schwarzschild radius is about 3 kilometers, or roughly 1.9 miles. Compress the Sun into a sphere 6 kilometers across, and it becomes a black hole, with space-time curved so extremely that light itself cannot escape. Stellar black holes. Stellar mass black holes form when massive stars run out of fuel and can no longer support themselves against their own gravity through nuclear fusion pressure. Stars spend most of their lives in a delicate balance. Gravity tries to compress them. The outward pressure from nuclear fusion in the core, where hydrogen fuses into helium and heavier elements, pushes outward and holds the star up against gravitational collapse. This balance can last billions of years for stars like our Sun, maintaining a stable equilibrium. But eventually the fuel runs out, the fusion reactions cease, and there's nothing left to hold the star up against its own gravity. For stars with initial masses above roughly 20 to 25 times our star's mass, the precise threshold, depending on composition and rotation, the core collapses catastrophically. The outer layers fall inward at speeds approaching 1/4 the speed of light, roughly 75,000 kilometers per second, or about 46,600 miles per second. When the infalling material hits the incompressible neutron core at the center, it rebounds, blasting back outward in a supernova explosion, one of the most energetic events in the universe. For a brief period lasting weeks, a single supernova can outshine an entire galaxy containing hundreds of billions of stars, pumping out more energy in that short time than our Sun will emit over its entire 10-billion-year lifetime. The explosion ejects most of the star's mass into space, seeding the interstellar medium with heavy elements forged in the star's core and in the supernova itself. All the carbon in your body, the oxygen you breathe, the iron in your blood, the calcium in your bones, all of it was created inside stars and scattered through space by supernova explosions billions of years ago. You are literally made of stardust, atoms forged in stellar furnaces and stellar deaths. But the core that's left behind after the supernova, if the original star was massive enough, collapses beyond even a neutron star's density. There's no known force or quantum pressure that can stop the collapse. The core shrinks past its Schwarzschild radius and becomes a black hole, vanishing behind an event horizon from which no information can ever return to the outside universe. These stellar mass black holes typically have masses between roughly 3 and 20 times our star's mass, concentrated in regions smaller than cities, but with gravitational pulls capable of shredding anything that approaches too close. Supermassive black holes. At the centers of most large galaxies, including our own Milky Way, lurk supermassive black holes with masses millions or even billions of times our star's mass. The supermassive black hole at the Milky Way's center, called Sagittarius A star, has a mass of approximately 4 million times our star's mass. That's over a trillion kilograms of mass compressed into a region smaller than Mercury's orbit around our star. Despite its enormous mass, Sagittarius A star is relatively quiet, not currently consuming large amounts of material and therefore not emitting much radiation from infalling matter, heating up as it spirals inward. Other galaxies host far more massive black holes, monsters with masses reaching billions of stellar masses. The galaxy Messier 87, roughly 54 million light-years away in the Virgo cluster, contains a supermassive black hole with a mass estimated at 6.5 billion times our star's mass. That black hole was the first ever directly imaged by the Event Horizon Telescope collaboration in 2019, a historic achievement in astronomy. The image shows a glowing ring of hot gas orbiting the black hole, with a dark shadow in the center representing the black hole's event horizon and the region just outside it where light can barely escape, often orbiting the black hole multiple times before spiraling inward or escaping outward. How do supermassive black holes form? Stellar mass black holes can't grow to millions or billions of stellar masses just by consuming gas and stars, because there are limits to how fast they can accrete matter based on radiation pressure from the infalling material, heating up and emitting intense radiation. That radiation pushes outward against infalling matter, creating a speed limit on accretion called the Eddington limit. Growing from 10 stellar masses to a billion stellar masses by accretion alone would take longer than the current age of the universe, roughly 13.8 billion years. Yet we observe supermassive black holes in galaxies less than a billion years after the Big Bang, when the universe was less than 10% of its current age. This is one of the major unsolved problems in astrophysics, a puzzle that challenges our understanding of black hole formation and growth. Perhaps supermassive black holes form directly from the collapse of enormous gas clouds in the early universe, skipping the stellar stage entirely and collapsing straight into massive black holes called direct collapse black holes. Perhaps they form from collisions and mergers of many smaller black holes in dense star clusters at galaxy centers, building up mass through cosmic collisions. Perhaps the early universe had conditions that allowed faster accretion rates than currently possible, allowing black holes to grow faster than the Eddington limit permits today. The answer remains uncertain, an active area of research with competing theories and ongoing observations trying to pin down the truth. Inside the event horizon, what happens if you fall into a black hole? The experience would be profoundly strange, dramatically different depending on the size of the black hole you're falling into. For a stellar mass black hole with a mass of maybe 10 times our star's mass, the event horizon is only about 30 kilometers or roughly 19 miles in radius. As you approach the event horizon, your feet closer to the black hole experience much stronger gravity than your head farther away. This difference in gravitational pull is called a tidal force, the same kind of force that creates ocean tides on Earth, but vastly stronger near a black hole. The tidal forces near a stellar mass black hole are enormous, so strong they would stretch your body vertically while compressing it horizontally, a process astrophysicists whimsically call spaghettification. Stretched like spaghetti. Long before you reach the event horizon, the tidal forces would rip apart your molecular bonds, then tear apart atoms themselves, reducing you to a stream of subatomic particles spiraling toward the singularity. You would die, experiencing perhaps the most violent death imaginable, torn apart by space-time curvature itself. But for a supermassive black hole like the one at the Milky Way's center, the situation is dramatically different. The event horizon radius scales with mass, so Sagittarius A star's event horizon is roughly 12 million kilometers, or about 7.5 million miles in radius. That's about 17 times the radius of our Sun, an enormous volume of space. The tidal forces at the event horizon of such a massive black hole are actually quite weak, gentle enough that you wouldn't immediately notice anything special as you crossed the point of no return. You could cross the event horizon alive, intact, still able to look around and observe your surroundings. Of course, you'd be doomed, with no hope of escape or rescue. All your possible futures would lead toward the singularity at the center, where space-time curvature becomes infinite, according to Einstein's equations, and the known laws of physics break down completely. You'd have perhaps minutes or hours before reaching the singularity, depending on the black hole's spin and your trajectory. But for that brief time, you could potentially observe the interior of the event horizon, witnessing phenomena no one has ever seen or could ever report back to the outside universe. What would you see? From inside the event horizon, looking outward, you'd see the entire future history of the universe outside compressed into a brief moment, time-dilated and blue-shifted. Light from distant stars and galaxies would pour in through a shrinking circle behind you, becoming increasingly concentrated and energetic as you fell deeper into the gravitational well. Looking toward the singularity ahead of you, you'd see nothing but darkness, perhaps punctuated by the radiation from other infalling matter that crossed the horizon before you, material caught in the same inescapable trap. And then you'd reach the singularity, where Einstein's equations predict infinite space-time curvature, infinite tidal forces, infinite density. At that point, general relativity itself breaks down, ceases to make valid predictions. The theory signals its own failure by producing infinities, mathematical impossibilities that indicate we're missing crucial physics. Most physicists believe that quantum mechanics, which Einstein's classical theory ignores, becomes crucially important at the singularity, preventing the true mathematical infinity through quantum effects we don't yet fully understand. But without a complete theory of quantum gravity, a framework that successfully merges general relativity with quantum mechanics, we cannot say for certain what happens at the singularity. It remains one of physics's deepest mysteries, a boundary where our theories fail and speculation takes over. Observing black holes. If nothing can escape from inside a black hole's event horizon, including light itself, how do we observe black holes? How do we know they exist if they're invisible by definition? Black holes themselves may be invisible, but their effects on surrounding matter and space-time are dramatic and observable with the right instruments. When matter falls toward a black hole, it doesn't fall straight in like water down a drain. It has angular momentum, rotational motion that must be conserved. The infalling matter forms an accretion disk, a swirling disk of gas and dust spiraling inward toward the event horizon. As material in the disk spirals inward, moving faster and faster as it approaches the black hole, friction between adjacent layers of the disk heats the gas to millions or even billions of degrees. Temperatures where atoms are fully ionized and electrons are stripped from nuclei. At these extreme temperatures, the gas emits intense radiation across the electromagnetic spectrum, from radio waves to X-rays and even gamma rays. The region just outside a black hole's event horizon can become one of the brightest objects in the universe, pumping out more energy per unit volume than almost any other astronomical phenomenon. The black hole itself emits nothing, remaining perfectly dark. But the superheated accretion disk blazes with incredible luminosity, a beacon visible across cosmic distances. By observing this radiation and studying how it varies over time, how it flickers and changes as clumps of matter spiral inward, astronomers can infer the presence of a black hole and even measure its mass and spin. X-ray telescopes in space, orbiting above Earth's atmosphere which blocks most X-ray radiation, have detected thousands of stellar mass black holes in binary systems throughout our galaxy. Systems where a normal star orbits an invisible companion that's pulling material away from the star and heating it to X-ray emitting temperatures. Some of the best evidence for black holes comes from tracking the orbits of stars near the centers of galaxies. At the Milky Way's center, astronomers have monitored individual stars orbiting the supermassive black hole Sagittarius A star for over 20 years now, carefully measuring their positions year after year. One star called STU has been observed for a complete orbit around the black hole, taking roughly 16 years to complete one circuit. STU's orbit is highly elliptical, bringing it as close as 17 light-hours from the black hole at its closest approach. Moving at speeds exceeding 5,000 kilometers per second, or about 3,000 miles per second, roughly 1.7% of light speed. By tracking STU's orbit and applying Kepler's laws modified by general relativity, astronomers calculated that the central object has a mass of approximately 4 million solar masses concentrated in a region smaller than Mercury's orbit. There's no known object other than a black hole that could pack that much mass into such a small volume without collapsing into a black hole anyway. The observations essentially prove that Sagittarius A star is a supermassive black hole, confirming decades of theoretical predictions with direct observational evidence. The first black hole image. In 2019, the Event Horizon Telescope collaboration announced they had captured the first-ever image of a black hole's event horizon, a historic achievement representing decades of technological development and international cooperation. The target was the supermassive black hole at the center of the galaxy Messier 87, chosen because despite being 54 million light-years away, its enormous mass of 6.5 billion solar masses makes its event horizon large enough to resolve with sufficiently high angular resolution. How do you image something 54 million light-years away? The angular size of M87's event horizon, as seen from Earth, is roughly 40 microarcseconds, an unimaginably tiny angle. That's like trying to see a grapefruit on the Moon's surface from Earth, resolving details far beyond what any single telescope can achieve, regardless of size. The resolution of a telescope is limited by diffraction, fundamentally constrained by the ratio of the wavelength observed to the telescope's diameter. To achieve 40 microarcsecond resolution observing at millimeter wavelengths, you'd need a telescope roughly the diameter of Earth itself. That's exactly what the Event Horizon Telescope collaboration built. In a sense, they created a virtual Earth-sized telescope using a technique called very long baseline interferometry. 8 radio telescopes scattered across the planet, from Hawaii to Chile to Antarctica, observed M87 simultaneously over several nights in April 2017. Each telescope recorded the incoming radio waves, along with precision timestamps from atomic clocks. Later, the recorded data from all telescopes was combined, synchronized using the atomic clock timestamps, effectively creating a single telescope with a diameter equal to the maximum separation between observatories, roughly the diameter of Earth. The computational challenges were enormous. The telescopes generated petabytes of data, so much information it had to be physically shipped on hard drives, because transferring it over the internet would take longer than flying it across the world. Months of computation on supercomputers were required to process the data, combining the signals and reconstructing an image from the interferometric measurements. The result was worth the wait. The image shows a glowing ring of orange-yellow light surrounding a dark central region, the black hole's shadow. The ring is the emission from hot gas in the accretion disk, orbiting at significant fractions of light speed just outside the event horizon. The dark central shadow represents the event horizon itself and the region just beyond it, where photons can orbit the black hole temporarily before either escaping or falling in, creating a zone of darkness roughly 2.5 times the size of the actual event horizon. The image precisely matches predictions from general relativity, confirming Einstein's century-old equations in one of the most extreme gravitational environments in the universe. In 2022, the collaboration announced a second black hole image, this time of Sagittarius A star at our own galaxy's center. Despite being over 2,000 times closer than M87, at only 26,000 light-years away, Sagittarius A star proved harder to image because of its much smaller mass. The gas in its accretion disk orbits in minutes rather than days, creating a rapidly changing environment that blurs over the hours-long observation period. The team had to develop new techniques to account for this variability, essentially creating thousands of possible images and averaging them to reveal the underlying structure. The resulting image shows a similar glowing ring with a dark central shadow, further confirming black hole predictions. Gravitational waves, ripples in spacetime. If massive objects curve spacetime, what happens when those objects move, especially when they accelerate or orbit each other? They create ripples in spacetime itself, disturbances that propagate outward at the speed of light, carrying energy and information about the events that created them. Einstein predicted these gravitational waves in 1916, just a year after publishing General Relativity, working out the mathematics of how moving masses would create wave-like distortions in space-time geometry. For most everyday situations, gravitational waves are incredibly weak, undetectably tiny even with the most sensitive instruments imaginable. Earth orbiting the Sun produces gravitational waves, but they're so weak that they carry away only about 200 watts of energy, roughly the power of 2 incandescent light bulbs. That's utterly negligible compared to Earth's total orbital energy, which would take longer than the age of the universe to significantly decay due to gravitational wave emission. You could never detect gravitational waves from Earth's orbit, even in principle with perfect instruments. But when truly massive objects move at significant fractions of light speed in strong gravitational fields, the gravitational wave emission becomes substantial, strong enough to potentially detect across cosmic distances. The best sources are pairs of compact objects, like black holes or neutron stars, orbiting each other in tight binary systems, spiraling inward as gravitational wave emission carries away their orbital energy, accelerating their death dance until they finally merge in a violent collision. The LIGO discovery. For decades, physicists worked to build detectors sensitive enough to catch gravitational waves, attempting to measure distortions in space-time so tiny they defy intuition. The challenge is extraordinary. A gravitational wave passing through Earth stretches and squeezes space itself, but by an almost impossibly small amount. A strong gravitational wave from a merging black hole binary might change the distance between 2 points by a part in 10 to the 21st, 1 part in a billion trillion. For 2 points separated by 4 kilometers or about 2.5 miles, the distance change is roughly 1/10,000th the diameter of a proton, the nucleus of a hydrogen atom. The Laser Interferometer Gravitational Wave Observatory, LIGO for short, was designed to detect exactly these tiny distortions using laser interferometry. LIGO consists of 2 facilities, one in Hanford, Washington, and one in Livingston, Louisiana, separated by roughly 3,000 kilometers, or about 1,900 miles. Each facility houses an L-shaped interferometer with arms 4 kilometers long, roughly 2.5 miles, the longest vacuum systems ever built. Laser light travels back and forth through the vacuum tubes, bouncing between mirrors, and the light from both arms recombines at a detector. When space-time is undisturbed, flat and calm, the interferometer is carefully adjusted so that the light from the 2 arms destructively interferes, cancelling out to produce darkness at the detector. But when a gravitational wave passes through, it stretches space in one direction, while simultaneously squeezing it in the perpendicular direction, changing the relative lengths of the 2 arms by that tiny fraction of a proton diameter. That microscopic length change shifts the relative phase of the light in the 2 arms, causing the destructive interference to become incomplete, allowing some light to reach the detector. By measuring that light intensity variation over time as the gravitational wave passes through, rippling space-time like waves on a pond, LIGO can reconstruct the gravitational wave signal. On September 14, 2015, both LIGO detectors observed a signal that swept upward in frequency over 1/5 of a second, a characteristic chirp pattern exactly matching theoretical predictions for 2 black holes spiraling together and merging. The signal reached LIGO Livingston 7 milliseconds before LIGO Hanford, consistent with a gravitational wave traveling at light speed from a source located in the southern sky. Analysis of the signal revealed that 2 black holes, with masses of approximately 36 and 29 solar masses, had orbited each other, spiraled inward as gravitational waves carried away their orbital energy, and finally merged into a single black hole of roughly 62 solar masses. Wait, let's do the math. 36 plus 29 equals 65. But the final black hole has only 62 solar masses. What happened to the missing 3 solar masses? Roughly 6 times 10 to the 30th kilograms of matter vanished from the final accounting. That mass was converted entirely into gravitational wave energy, using Einstein's famous equation relating mass and energy. 3 solar masses worth of energy was pumped into gravitational waves in the final fraction of a second before merger, making this event briefly the most energetically luminous phenomenon in the observable universe, emitting more power in gravitational waves than all the stars in all the galaxies in the visible universe combined radiate in light. For that brief moment, this collision of 2 black holes over 1 billion light-years away dominated the universe's energy output. The detection was announced in February 2016, after months of careful analysis to confirm it wasn't some instrumental artifact or environmental noise. The announcement made headlines worldwide, marking the first direct detection of gravitational waves and the first direct observation of black holes merging, confirming predictions Einstein made a century earlier. Three leaders of the LIGO collaboration, Rainer Weiss, Barry Barish, and Kip Thorne, received the 2017 Nobel Prize in Physics for the discovery and decades of work developing gravitational wave astronomy. More gravitational wave detections. Since that first historic detection, LIGO and its partner detector Virgo in Italy have observed dozens of gravitational wave events, building a catalogue of black hole and neutron star mergers throughout the universe. Each detection provides a unique test of general relativity under extreme conditions, checking whether the waves propagate at light speed, whether they have the predicted polarizations, whether their waveforms match theoretical templates calculated from Einstein's equations. So far, every observation has confirmed general relativity's predictions with remarkable precision, showing no deviations from Einstein's theory. Even in situations involving black holes with masses dozens of times larger than our Sun, moving at significant fractions of light speed. General relativity, formulated over a century ago with pencil and paper, continues to accurately describe the universe's most extreme gravitational phenomena. One particularly exciting detection occurred on August 17, 2017, when LIGO and Virgo observed gravitational waves from two neutron stars merging, each with a mass between 1 and 2 solar masses. Unlike black holes, neutron stars are made of matter, incredibly dense matter, where protons and electrons are crushed together into neutrons, but matter nonetheless. When neutron stars collide, they don't just merge cleanly. They create spectacular fireworks visible across the electromagnetic spectrum. Within 2 seconds of the gravitational wave detection, the Fermi Gamma Ray Space Telescope detected a brief burst of gamma rays from the same region of sky, confirming that the collision had indeed produced electromagnetic radiation. Over the following hours and days, dozens of telescopes around the world and in space observed the collision's afterglow across all wavelengths, from radio waves to X-rays, watching the aftermath as radioactive debris ejected from the collision glowed and faded. This was the first time a cosmic event had been observed in both gravitational waves and electromagnetic radiation, the birth of multi-messenger astronomy, combining gravity wave observations with traditional telescope observations. The observations confirmed long-standing theories that neutron star mergers are a primary site for creating heavy elements like gold and platinum through rapid neutron capture nucleosynthesis, a process called the R process. The collision ejected perhaps 1/100th of a solar mass of material enriched with these heavy elements, seeding the universe with the raw materials for future planets and life. The gold in any jewelry you own was almost certainly created in a neutron star merger billions of years ago, forged in conditions of unimaginable density and temperature. Dark matter, the invisible majority. General relativity describes how mass and energy curve space-time, but it turns out that most of the mass in the universe isn't the ordinary matter we're familiar with. When astronomers measure how fast stars orbit in galaxies or how fast galaxies move within galaxy clusters, they find that visible matter, the stars and gas we can see through telescopes, doesn't produce nearly enough gravity to explain the observed motions. Something invisible, something that doesn't emit or absorb light, but does exert gravitational influence, must be present in huge quantities. This mysterious substance is called dark matter. Invisible not because it's literally dark, but because it doesn't interact with electromagnetic radiation at all, passing through normal matter almost entirely unaffected. Dark matter makes up approximately 27% of the universe's total mass energy content, compared to only about 5% for ordinary matter. The protons and neutrons and electrons that make up atoms and everything built from atoms. Dark matter outweighs ordinary matter by more than 5 to 1. making the stuff we're made of a small minority component in the cosmic inventory. How do we know dark matter exists if we can't see it? The evidence comes from multiple independent observations that all point to the same conclusion. First, galaxy rotation curves, graphs showing how fast stars orbit at different distances from a galaxy's center. Based on visible matter alone, stars far from a galaxy's center should orbit slower, following Kepler's laws just like planets in our solar system, where outer planets orbit slower than inner planets. But observations show that rotation speeds remain roughly constant out to the edges of galaxies, staying flat rather than declining as expected. The only explanation that fits the data is that galaxies are embedded in massive halos of dark matter extending far beyond the visible disk, providing additional gravity that keeps the outer stars moving faster than visible matter alone would predict. The dark matter halos are roughly 10 times more massive than the visible galaxy, dominating the gravitational dynamics. Second, gravitational lensing observations show that the total mass in galaxy clusters, measured by how much they bend light from background galaxies, far exceeds the mass of visible matter. The bullet cluster, formed from two galaxy clusters that collided and passed through each other, provides particularly compelling evidence. The hot gas visible in X-rays was slowed by the collision, piling up between the two clusters. But gravitational lensing measurements show that most of the mass is located where the galaxies themselves are, separated from the gas. The dark matter passed through the collision essentially unaffected, not interacting with itself or the gas, while the normal matter gas was slowed by electromagnetic interactions. This separation of visible matter from the gravitational mass distribution is difficult to explain without invoking dark matter as a distinct component that doesn't interact electromagnetically. Third, observations of the cosmic microwave background radiation, the faint afterglow of the Big Bang filling all of space, show patterns that only make sense if roughly 27% of the universe's mass energy is dark matter. The slight temperature variations in the cosmic microwave background, deviations of only a few parts per 100,000 from perfect uniformity, encode information about the matter composition of the early universe. Computer simulations that include dark matter reproduce the observed patterns almost perfectly. Simulations without dark matter fail to match the data, producing patterns incompatible with observations. Fourth, the large-scale structure of the universe, the way galaxies are distributed in enormous filaments and sheets surrounding vast voids, reflects the influence of dark matter in the early universe. Dark matter began clumping under its own gravity long before ordinary matter could, because ordinary matter was initially too hot and pressure-supported to collapse. Dark matter doesn't feel electromagnetic forces, so it doesn't experience pressure from photons or thermal pressure from collisions, allowing it to collapse earlier. These dark matter clumps then acted as gravitational seeds, attracting ordinary matter and forming the scaffolding upon which galaxies eventually formed. Computer simulations, including dark matter, produce cosmic web structures remarkably similar to what large galaxy surveys observe, matching the statistical properties of how galaxies cluster across billions of light-years. What is dark matter? Despite overwhelming evidence that dark matter exists and makes up most of the universe's mass, we still don't know what it actually is at the particle physics level. It's not ordinary matter made of protons and neutrons, because we can account for essentially all the ordinary matter through various observations. If there were 5 times more ordinary matter than we observe, floating around invisibly, it would affect Big Bang nucleosynthesis predictions for hydrogen and helium abundances, predictions that match observations only if ordinary matter comprises roughly 5% of the universe. Leading candidates for dark matter are hypothetical particles that interact only through gravity and possibly the weak nuclear force, not through electromagnetism or the strong nuclear force. These are sometimes called WIMPs, weakly interacting massive particles. If WIMPs exist with masses, perhaps 10 to 1,000 times the proton mass and appropriate interaction strengths, they would have been produced in the early universe in abundances matching dark matter observations today. They would have survived to the present. moving through space, essentially invisible except for their gravitational effects. Numerous experiments have searched for dark matter particles directly by building ultra-sensitive detectors deep underground, shielded from cosmic ray interference, waiting for the incredibly rare event where a dark matter particle from the galactic halo collides with a detector atom. Despite decades of searching with increasingly sensitive instruments, no confirmed dark matter particle detection has been made yet. The lack of detections rules out some proposed particle properties, but hasn't eliminated all possibilities. Dark matter might interact even more weakly than initially expected, requiring even larger or more sensitive detectors than currently exist. Alternative theories propose that dark matter consists of primordial black holes formed in the early universe from density fluctuations before the first stars formed, or that it's made of exotic particles called axions with masses billions of times smaller than electrons. Each proposal has supporting arguments and challenges, ongoing research attempting to pin down the truth. The nature of dark matter remains one of the most significant unsolved problems in physics, a fundamental question about the composition of the universe. Dark energy, the mysterious acceleration. If dark matter wasn't strange enough, astronomers discovered something even more mysterious in the late 1990s. Dark energy. Two independent teams of astronomers studying distant supernovae, stellar explosions that can be used as standard candles to measure cosmic distances, made a shocking discovery. The universe's expansion isn't just continuing from the initial Big Bang impulse. It's accelerating, speeding up over time rather than slowing down as expected. This discovery was completely unexpected, contradicting what most cosmologists anticipated. The universe contains matter and energy, and gravity from that matter should slow the expansion, potentially even eventually reversing it to cause a big crunch where everything collapses back together. But the observations showed the opposite. Something is pushing the expansion to accelerate, overcoming gravity's attractive pull. That something has been named dark energy. Though the name reveals our ignorance more than our understanding, we know it's dark, invisible to telescopes. We know it has energy, affecting the universe's expansion, but we don't know what it actually is. Dark energy appears to dominate the universe's mass-energy budget, making up approximately 68% of the total. Combined with dark matter at 27%, that leaves only 5% for ordinary matter, everything we can see and touch and build instruments from. We are the minority component in a universe dominated by substances we don't understand, a humbling realization that reveals how much remains unknown. The simplest explanation for dark energy is Einstein's cosmological constant, a term Einstein himself added to his field equations in 1917 and later called his biggest blunder. Einstein initially believed the universe should be static, neither expanding nor contracting, eternal and unchanging. But his original equations predicted an unstable universe that would either expand or collapse. To make a static universe possible, he added a constant term, representing a uniform energy density filling all of space, providing a repulsive effect to balance gravity's attraction. When Edwin Hubble discovered in 1929 that the universe is actually expanding, with galaxies moving away from each other with speeds proportional to their distances, Einstein realized the cosmological constant was unnecessary. A universe that began expanding from the Big Bang would naturally continue expanding due to that initial motion, requiring no additional physics to explain. Einstein reportedly abandoned the cosmological constant, considering it a mistake motivated by incorrect assumptions about the universe's behavior. But the cosmological constant has made a comeback as the leading explanation for dark energy. In modern understanding, the cosmological constant represents vacuum energy, the intrinsic energy of empty space itself. Quantum field theory predicts that even completely empty space should have energy due to quantum fluctuations, virtual particles constantly appearing and disappearing from the vacuum. This vacuum energy would have exactly the properties needed to explain dark energy observations, it's uniformly distributed throughout space. It doesn't dilute as the universe expands, because new space created by expansion contains the same vacuum energy density, and it causes a repulsive gravitational effect accelerating expansion. The cosmological constant problem. However, there's a massive problem. When physicists try to calculate how much vacuum energy quantum field theory predicts, they get an answer roughly 10 to the 120 times larger than the observed dark energy density. That's one followed by 120 zeros, an incomprehensibly huge discrepancy. It's arguably the worst prediction in the history of physics, the largest disagreement between theory and observation ever encountered. Something is wrong, either with our understanding of quantum field theory, our understanding of gravity, or both. Some unknown mechanism must cancel out almost all the predicted vacuum energy, leaving behind only the tiny amount we observe as dark energy. But physicists have no idea what that mechanism might be, or why it would leave behind precisely the small amount observed, rather than cancelling everything completely. This is called the cosmological constant problem, and despite decades of theoretical work, no satisfactory solution has been found. It represents a fundamental gap in our understanding of how quantum mechanics and gravity fit together. Alternative explanations for dark energy propose that it's not a cosmological constant, but rather some dynamic field that changes over time, sometimes called quintessence after the classical fifth element beyond Earth: water, air, and fire. If dark energy is quintessence, its density might vary over cosmic history, potentially increasing or decreasing as the universe ages. Different quintessence models make different predictions for how the universe's expansion rate changes over time. Predictions that could potentially be tested with sufficiently precise astronomical observations of distant supernovae and galaxies. Another possibility is that general relativity itself breaks down on cosmological scales, that Einstein's equations need modification when applied to the universe as a whole. Modified gravity theories attempt to reproduce dark energy's effects by changing how gravity behaves over enormous distances or in regions of very low space-time curvature. These theories face significant challenges, matching all observations, particularly the detailed structure of the cosmic microwave background and the growth of cosmic structure over time. But research continues exploring whether modified gravity could eliminate the need for dark energy entirely. Cosmology and the universe's history. General relativity provides the framework for understanding cosmology, the study of the universe as a whole, its origin, evolution, and ultimate fate. Einstein's equations applied to a homogeneous, isotropic universe, one that looks roughly the same everywhere and in all directions when averaged over sufficiently large scales, lead to specific predictions about how the universe expands over time, depending on its energy and matter content. The universe began in an extremely hot, dense state, roughly 13.8 billion years ago, in the event we call the Big Bang. Not an explosion in space, but an expansion of space itself, carrying matter and energy along with it. Every point in space is moving away from every other point on cosmological scales, with no special center or edge. If you could rewind cosmic history, you'd see galaxies getting closer together, the universe getting denser and hotter, approaching a state of nearly infinite density and temperature at the beginning. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion called cosmic inflation, where space expanded faster than light by an enormous factor in an incredibly brief time. Inflation was driven by a hypothetical field called the inflaton, similar in some ways to dark energy but much stronger. Inflation explains several puzzles about the observed universe. Why regions of space separated by vast distances that couldn't have been in contact since the Big Bang have almost identical temperatures? Why the universe is so geometrically flat rather than curved like a saddle or sphere? And why we don't observe exotic relics like magnetic monopoles predicted by particle physics theories. After inflation ended, the universe continued expanding but at a much slower rate, filled with an incredibly hot soup of fundamental particles. As the universe expanded and cooled, particles combined into protons and neutrons, then into the first atomic nuclei through Big Bang nucleosynthesis, when the universe was roughly 3 minutes old. Roughly 3/4 of ordinary matter by mass ended up as hydrogen nuclei, simple protons. Most of the remaining quarter became helium-4 nuclei with trace amounts of deuterium, helium-3, and lithium-7. These predicted abundances match observations of the oldest stars and gas clouds extremely well, providing strong evidence for the Big Bang model. But the universe remained too hot for atoms to form, with free electrons scattered throughout space. These free electrons scattered photons constantly, making the universe opaque like a thick fog. Light couldn't travel far before hitting an electron and scattering in a different direction. Only when the universe cooled to roughly 3,000 degrees Kelvin, about 380,000 years after the Big Bang, could electrons combine with nuclei to form neutral atoms in a process called recombination. With free electrons locked into atoms, photons could suddenly travel freely through space without constant scattering. The universe became transparent, filled with glowing gas at 3,000 degrees. The cosmic microwave background. Those photons from recombination have been traveling through space ever since, stretched to longer wavelengths by the universe's expansion. Photons that started as visible or infrared light with wavelengths around 1 micrometer have been stretched by a factor of roughly 1,100 to wavelengths around 1 millimeter, shifting them into the microwave portion of the spectrum. This is the cosmic microwave background radiation discovered accidentally in 1964 by Arno Penzias and Robert Wilson, earning them the 1978 Nobel Prize in Physics. The cosmic microwave background fills all of space with nearly uniform microwave radiation at a temperature of 2.725 degrees Kelvin, just under 3 degrees above absolute zero. It's the oldest light in the universe, a snapshot of what the cosmos looked like when it was only 380,000 years old, less than 1/40,000th of its current age. By studying the cosmic microwave background in exquisite detail, with satellites like the Cosmic Background Explorer in the 1990s, the Wilkinson Microwave Anisotropy Probe in the 2000s, and the Planck satellite from 2009 to 2013, cosmologists have measured the universe's properties with remarkable precision. The cosmic microwave background isn't perfectly uniform. It has tiny temperature variations, deviations of only about 1 part in 100,000 from the average temperature. These variations represent density fluctuations in the early universe, regions that were slightly denser or less dense than average. Quantum fluctuations from the inflation era stretch to cosmic scales. The pattern of these variations encodes enormous amounts of information about the universe: its age, its geometry, its matter and energy content, the properties of dark matter and dark energy. Analysis of cosmic microwave background data tells us the universe is 13.8 billion years old, give or take a few tens of millions of years. It tells us the universe is geometrically flat, meaning parallel lines extended infinitely would never converge or diverge. It tells us ordinary matter makes up 4.9% of the universe's mass energy. Dark matter makes up 26.8%, and dark energy makes up 68.3%. These measurements are so precise that they've transformed cosmology from a field of rough estimates and order of magnitude calculations into a precision science, with measurements accurate to percent level, better, structure formation. After recombination, the universe entered what's called the cosmic dark ages, a period lasting perhaps several 100 million years, when no stars yet existed and the universe was filled only with neutral hydrogen and helium gas. The density fluctuations visible in the cosmic microwave background continued growing under gravity's influence. Dark matter clumped together first, forming gravitational potential wells. Ordinary matter, freed from radiation pressure after recombination, fell into those dark matter wells, accumulating in regions destined to become galaxies. Eventually, the gas density in the densest regions became high enough that gravity overcame internal pressure, causing the gas to collapse and fragment. The first stars formed, probably between 100 million and 400 million years after the Big Bang, ending the Dark Ages. These first stars were likely very massive, perhaps 100 to 1,000 times our Sun's mass, formed from pristine hydrogen and helium with no heavier elements. They burned incredibly hot and bright, living only a few million years before exploding as supernovae, enriching the interstellar medium with the first heavy elements forged in stellar cores and supernova nucleosynthesis. The first star's ultraviolet light began ionizing the neutral hydrogen throughout the universe, creating expanding bubbles of ionized gas around each star and galaxy. Over roughly the next billion years, this process called reionization gradually ionized essentially all the hydrogen in the universe, returning it to an ionized state, similar to before recombination, but now at much lower density due to cosmic expansion. The universe became transparent to ultraviolet light, allowing us to observe very distant galaxies that would otherwise be hidden behind absorbing neutral hydrogen. Galaxies formed through a hierarchical process, small structures forming first and then merging together into larger structures over time. The smallest dark matter halos formed galaxies first, while larger halos took longer to collapse and form galaxies. These early galaxies often collided and merged, building larger galaxies like our Milky Way. The Milky Way itself has grown through mergers, consuming dozens of smaller satellite galaxies over its history, and even now is in the process of absorbing several dwarf galaxies. In roughly 4 billion years, the Milky Way will collide and merge with the Andromeda Galaxy, our nearest large galactic neighbor, forming a larger elliptical galaxy, sometimes called Milkomeda, the universe's ultimate fate. What will happen to the universe in the distant future? The answer depends primarily on dark energy's behavior. If dark energy is truly a cosmological constant with fixed density, as current observations suggest, the universe will continue accelerating its expansion forever. Galaxies outside our local group, the small cluster containing the Milky Way and Andromeda, along with dozens of smaller galaxies, will gradually move away from us faster and faster, eventually receding faster than light can travel through space. Light from those galaxies will become increasingly redshifted, dimmer, and slower to arrive until eventually it stops reaching us altogether. Within roughly 150 billion years, every galaxy beyond our local group will disappear from view, forever beyond our observable universe's horizon. Stars will continue forming as long as galaxies contain cold gas reserves, but eventually those reserves will be exhausted. The universe will grow darker as existing stars age and die, without being replaced by new stellar generations. The longest-lived stars, small red dwarfs with masses around 1/10 our Sun's mass, can burn for trillions of years, over 100 times the current age of the universe. But eventually, even these miserly stars will exhaust their hydrogen fuel, fading to cold black dwarfs, stellar remnants no longer generating energy through fusion. By roughly 100 trillion years from now, 100,000 times the universe's current age, essentially all stars will have burned out. Galaxies will be dark collections of stellar remnants, white dwarfs, neutron stars, black holes, brown dwarfs that never achieved fusion, and planets wandering through eternal night. Even these remnants won't last forever. Over timescales of 10 to the 30 years or longer, stellar remnants will gradually lose orbital energy through gravitational wave emission during rare close encounters, causing them to slowly spiral into the supermassive black holes at galaxy centers. Eventually, galaxies themselves will evaporate as stars are occasionally ejected through gravitational interactions, scattered to wander intergalactic space alone. If protons are unstable, as some theories predict, they will eventually decay into lighter particles over timescales of perhaps 10 to the 34 years or longer, a number so vast it's essentially meaningless in human terms. All atomic nuclei would gradually disintegrate, transforming matter into radiation and exotic particles. Even if protons are perfectly stable, matter would eventually be consumed by black holes or scattered to vast distances through gravitational interactions, leaving the universe as an increasingly dilute sea of radiation and isolated particles. Black hole evaporation and the ultimate end. Even black holes won't last forever. Stephen Hawking showed in 1974 that black holes should emit radiation due to quantum effects near the event horizon, a phenomenon now called Hawking radiation. Virtual particle-antiparticle pairs constantly pop into existence from the vacuum due to quantum uncertainty. Normally, these pairs annihilate almost instantly, returning the borrowed energy to the vacuum. But near a black hole's event horizon, occasionally one particle falls into the black hole while the other escapes to infinity. From an external perspective, this looks like the black hole emitting particles and radiation, slowly losing mass over time. The process is incredibly slow for large black holes. A black hole with our Sun's mass would take roughly 10 to the 67 years to evaporate completely, emitting Hawking radiation at an average temperature of only about 60 nanokelvins, far colder than the current cosmic microwave background. A supermassive black hole with 1 billion solar masses would take 10 to the 98 years to evaporate, an incomprehensible duration far exceeding anything we can meaningfully contemplate. But eventually, given enough time, all black holes will evaporate through Hawking radiation. The smaller a black hole becomes, the hotter it grows and the faster it evaporates, accelerating exponentially in the final stages. A black hole's final moments would be spectacular, exploding in a burst of radiation as the last remnant of mass converts to energy. After the last black hole evaporates, perhaps 10 to the 100 years from now, or even longer depending on the most massive black hole's sizes, the universe will contain only a dilute gas of elementary particles and photons, growing ever colder and more dispersed as expansion continues. This scenario is called heat death, not because the universe gets hot, but because it reaches maximum entropy, maximum disorder, with energy uniformly distributed at extremely low temperature. No structures remain, no gradients exist to drive energy flow, no processes can occur. The universe becomes static and featureless, continuing to expand and cool toward absolute zero temperature, but never quite reaching it. Time becomes meaningless in a universe where nothing changes, where no events mark the passage of time. This is the ultimate fate of the universe under current cosmological understanding, assuming dark energy remains constant and our theories are correct. Alternative fates and uncertainties. However, uncertainty remains about dark energy's future behavior. If dark energy's density increases over time, rather than remaining constant, a scenario sometimes called phantom energy, the accelerating expansion could eventually become so violent that it tears apart increasingly small structures. First, galaxy clusters would be ripped apart as expansion overcomes their gravitational binding. Then individual galaxies would dissolve as stars are pulled away faster than their orbital speeds. Eventually, even solar systems would be torn apart, then planets, then molecules, then atoms, and finally even atomic nuclei would be ripped apart by the ever-accelerating expansion. This scenario is called the Big Rip, predicted to occur perhaps 20 billion years from now, or longer depending on how rapidly dark energy strengthens. Everything in the universe would be shredded by expansion in the final moments before space-time itself possibly ceases to have meaning. Current observations show no evidence that dark energy is strengthening over time, suggesting the Big Rip is unlikely, but we cannot completely rule it out based on available data. Alternatively, if dark energy weakens or reverses over time, the universe's expansion could eventually slow and reverse, causing everything to collapse back together in a big crunch, the time-reversed opposite of the Big Bang. The universe would grow denser and hotter as galaxies crashed together and merged. Eventually, stars would be unable to cool as ambient temperature exceeded stellar surface temperatures. Ultimately, everything would converge to infinite density in a singularity, possibly followed by a new Big Bang in a cyclical universe that expands and contracts repeatedly over eternity. But again, observations show no indication that dark energy is weakening, making this scenario appear unlikely based on current evidence. Practical applications of general relativity. Beyond its profound implications for cosmology and our understanding of the universe's nature, general relativity has practical applications that affect everyday life in modern technological civilization. We've already discussed GPS, which requires relativistic corrections to function accurately, confirming Einstein's predictions billions of times daily. But there are other applications, some obvious and others subtle, where relativity matters for practical technology. Particle accelerators, like the Large Hadron Collider at CERN, accelerate protons to speeds exceeding 99.99999% of light speed. Energy so high that the proton's mass increases by a factor of over 7,000 due to special relativistic effects. The accelerator's magnets must be designed accounting for this mass increase, bending particles that are thousands of times heavier than their rest mass. Without relativistic calculations, the beams would crash into the accelerator walls, instead of circulating smoothly, making experiments impossible. Nuclear power and nuclear weapons both rely on mass-energy equivalence. Einstein's equation relating mass and energy. When uranium or plutonium undergoes fission, splitting into lighter nuclei, the total mass of the products is slightly less than the original nucleus's mass. That missing mass, roughly 0.1% of the original mass, is converted entirely into energy, according to Einstein's equation, producing the enormous power output of nuclear reactors and weapons. Without understanding that mass and energy are interconvertible, nuclear technology would be impossible. Electromagnetic generators and motors operate based on principles that are more naturally understood through special relativity. When you move a conductor through a magnetic field, electrons in the conductor experience a force, generating electric current. But from the electrons' perspective, in their own reference frame, they're stationary while the magnetic field source is moving. The force they experience appears to be electric rather than magnetic. Special relativity shows that electric and magnetic fields are different aspects of the electromagnetic field, with what appears electric or magnetic depending on your reference frame. Understanding this unification helps engineers design more efficient motors and generators. Relativistic effects in chemistry and materials. Even chemistry and materials science are affected by relativity, though most chemists rarely think about it explicitly. Gold's characteristic yellow color, unique among metals, results partly from relativistic effects on its electron orbitals. The innermost electrons in gold atoms orbit so close to the nucleus, where the electric field is extremely strong, that they reach significant fractions of light speed. Special relativity causes these electrons' mass to increase, contracting their orbital radius. This contraction affects the outer electrons through quantum mechanical screening effects, changing the energy levels and making gold absorb blue light, reflecting the complementary yellow color we see. Mercury is liquid at room temperature, unusual for a metal, partly because of similar relativistic effects contracting its electron orbitals and weakening metallic bonding between atoms. Lead is much denser than its lighter neighbors in the periodic table, partly because relativistic contraction of inner electron orbitals allows the atom to pack more tightly. These effects are subtle, typically contributing a few percent to various properties, but they're measurable and important for precise predictions of material behavior. In extremely powerful magnetic fields, such as those near magnetars, neutron stars with magnetic field strengths of 10 to the 14 Gauss or higher, quantum electrodynamics and relativistic effects cause vacuum itself to become birefringent, refracting light differently depending on its polarization. The vacuum essentially becomes optically active like a crystal, bending light paths and rotating polarization. Observations of magnetars show evidence for these vacuum effects, confirming exotic predictions from quantum field theory in curved spacetime. Gravitational wave astronomy's future. Gravitational wave astronomy is still in its infancy, with enormous potential for future discoveries. Current detectors like LIGO and Virgo are sensitive primarily to black holes and neutron stars, with masses between 1 and 100 times our Sun's mass, merging at distances up to several billion light-years. Future ground-based detectors will push sensitivity higher, observing more distant events and detecting weaker signals from less massive objects. The proposed Einstein telescope in Europe and Cosmic Explorer in the United States would have arms 10 kilometers long, about 6 miles, more than twice LIGO's arm length, and would use advanced technologies to reduce noise. These next-generation detectors could observe stellar mass black hole mergers across the entire observable universe, seeing back to when the universe was only a few 100 million years old and the first black holes were forming. They could detect neutron star mergers in such detail that gravitational waves alone could reveal internal structure, probing matter at densities exceeding atomic nuclei, where our understanding of physics becomes uncertain. Space-based gravitational wave detectors would open entirely new observation windows. The Laser Interferometer Space Antenna, LISA, planned for launch in the 2030s, will consist of 3 spacecraft flying in a triangular formation separated by 2.5 million kilometers, about 1.6 million miles. Free from Earth's seismic noise and able to maintain much longer arm lengths than ground-based detectors, LISA will observe lower-frequency gravitational waves from sources inaccessible to LIGO. LISA will detect supermassive black hole mergers throughout cosmic history, watching as black holes millions to billions of times our sun's mass spiral together over periods of months to years, providing advance warning before the merger and enabling coordinated observations with electromagnetic telescopes. It will observe intermediate mass black holes, objects with masses between 100 and 100,000 solar masses whose existence and properties remain uncertain. It will track compact binary stars within our own galaxy, detecting thousands of white dwarf binaries and neutron star binaries that emit gravitational waves at frequencies LIGO cannot observe. Perhaps most excitingly, LISA might detect gravitational waves from cosmic inflation itself, primordial gravitational waves generated in the first instance after the Big Bang and stretched to cosmic scales by inflation. Detecting these primordial waves would provide direct evidence for inflation, confirming a cornerstone prediction of modern cosmology and potentially revealing physics at energy scales trillions of times higher than particle accelerators can reach. The waves would carry information about the universe when it was only a tiny fraction of a second old, opening a window to physics at energies where quantum gravity effects might become important. Pulsar timing arrays. Another approach to gravitational wave detection uses pulsars, rapidly rotating neutron stars that emit radio pulses with extraordinary regularity. By precisely timing pulses from many pulsars scattered across the sky over periods of years or decades, astronomers can detect gravitational waves passing between Earth and the pulsars. The waves stretch and squeeze space, changing the distances to pulsars and causing pulse arrival times to shift slightly from the expected schedule. Pulsar timing arrays are sensitive to very low-frequency gravitational waves, with periods of months to years, even lower frequencies than LISA can observe. The primary expected sources are supermassive black hole binaries, with masses of hundreds of millions to billions of solar masses, orbiting each other for millions of years before finally merging. As galaxies merge throughout cosmic history, their central supermassive black holes eventually find each other and form binaries. The cumulative signal from all these binaries throughout the universe should create a stochastic background of gravitational waves, a continuous hum-filling space. Several pulsar timing array collaborations, including the North American Nanohertz Observatory for Gravitational Waves and the European Pulsar Timing Array, have been monitoring dozens of the most stable pulsars for over a decade, building up the timing precision needed to detect gravitational waves. Recent results hint at possible detection of the stochastic background, though confirmation requires more data. If confirmed, this would represent gravitational wave detection using an entirely different technique and frequency range, opening yet another window on the gravitational wave universe. Testing general relativity's limits. Despite general relativity's century of successful predictions, physicists continue searching for its limits, for situations where it might break down or require modification. We know relativity is incomplete because it doesn't incorporate quantum mechanics. At the singularities inside black holes and at the Big Bang, where densities and spacetime curvatures become infinite according to classical general relativity, quantum effects must become important. A complete theory of quantum gravity is needed to describe these extreme situations. But despite decades of effort, no complete quantum gravity theory has been confirmed. String theory proposes that fundamental particles are not point-like, but rather tiny vibrating strings, with different vibration modes corresponding to different particles. String theory naturally includes gravitons, hypothetical particles that mediate gravitational interactions, potentially providing a quantum description of gravity. But string theory requires extra spatial dimensions beyond the three we observe. Dimensions that must be compactified or hidden at extremely small scales. String theory also makes few testable predictions accessible to current experiments, making it difficult to confirm or refute despite its mathematical elegance. Loop quantum gravity takes a different approach, attempting to quantize space-time itself by describing it as a network of discrete loops at the Planck scale, roughly 10 to the negative 35 meters, about 10 to the negative 20 times smaller than a proton. At this scale, space-time becomes granular rather than continuous, with area and volume taking on discrete quantum values rather than varying smoothly. Loop quantum gravity might eliminate singularities, replacing them with quantum bounces or transitions, potentially explaining what happens at the center of black holes or at the Big Bang. But like string theory, loop quantum gravity faces challenges making testable predictions that could distinguish it from alternatives. Experimental tests of quantum gravity. Some physicists hope that observations of black holes, neutron stars, or the early universe might reveal quantum gravity effects, even without a complete theory. For example, if Hawking radiation is ever directly detected, it would provide experimental confirmation that quantum mechanics and gravity interact in ways not described by classical general relativity alone. Unfortunately, Hawking radiation from stellar mass or larger black holes is far too weak to detect with any conceivable technology, requiring us to wait for hypothetical primordial black holes with masses much smaller than our Sun, or to observe theoretical analogues in laboratory systems. Another possibility is that the extreme space-time curvature near black hole event horizons or during neutron star mergers might reveal subtle deviations from general relativity's predictions, deviations caused by quantum corrections or modifications to gravity at high curvature. Gravitational wave observations with current and future detectors provide opportunities to test general relativity in these extreme regimes with precision impossible before. So far, all gravitational wave observations match general relativity's predictions within measurement uncertainties, but future observations might reveal discrepancies pointing toward new physics. The cosmic microwave background might also encode signatures of quantum gravity from the inflation era. If inflation occurred at energy scales where quantum gravity effects were significant, those effects might leave imprints in the cosmic microwave background's temperature and polarization patterns. Detecting such signatures would provide indirect evidence for quantum gravity physics at energy scales, far beyond anything particle accelerators could ever reach, using the early universe as a laboratory for fundamental physics, wormholes, and time travel. General relativity allows some exotic solutions that have captured public imagination. Wormholes and time travel. A wormhole is a hypothetical tunnel connecting two distant regions of space-time through a shortcut through higher dimensional space. Instead of traveling the long way through normal space, you'd enter one mouth of the wormhole and emerge from the other mouth, potentially light years away, or even in a different time, after traveling only a short distance through the wormhole tunnel. Einstein and Nathan Rosen discovered the first wormhole solution to general relativity's equations in 1935, now called an Einstein-Rosen bridge. But these wormholes are unstable, collapsing before anything could travel through them, and they don't actually connect to different regions of the same universe, but rather connect to a parallel universe or different sheet of space-time. Later work showed that traversable wormholes, ones that don't collapse and do connect different parts of our universe, might be possible if exotic matter with negative energy density could hold them open against gravitational collapse. Quantum field theory does allow negative energy densities in limited circumstances through the Casimir effect. where two closely spaced metal plates in vacuum experience an attractive force because the vacuum between them has lower energy density than vacuum outside. But the total negative energy available through the Casimir effect is tiny, nowhere near enough to hold open a wormhole large enough for anything bigger than subatomic particles to pass through. Whether enough negative energy could be collected and stabilized to create a traversable wormhole remains unknown, with most physicists skeptical that it's possible. Even if traversable wormholes could exist, using them for time travel creates logical paradoxes. If you could travel back in time and prevent your own birth or alter the past in ways that contradict known history, you'd create inconsistencies in causality. The grandfather paradox, where you travel back and kill your grandfather before your parents were born, is the classic example. One resolution is the chronology protection conjecture, proposed by Stephen Hawking, suggesting that physical laws conspire to prevent time travel to the past, perhaps through quantum effects that destroy any incipient time machine before it can function. Another possibility is that backward time travel is possible, but only along self-consistent paths, trajectories that don't create paradoxes, because everything that happens when you travel back was always part of history. Any actions you take in the past were already baked into the timeline, creating a loop but not a contradiction. You can't change the past because you didn't change it. You were always part of it. This interpretation preserves logical consistency, but eliminates free will in time travel scenarios, forcing travelers to play out predetermined roles in history. Most physicists consider time travel and wormholes to be fascinating theoretical possibilities that probably remain forever in the realm of speculation rather than practical technology. The energy requirements, the need for exotic matter, the potential for causality violations, and quantum effects that might prevent their formation all suggest that even if the mathematics allows these solutions, physical reality probably doesn't permit their actual existence. But the fact that general relativity's equations allow such exotic possibilities demonstrates how strange and counterintuitive the theory is, how far it departs from everyday intuition about space and time, gravitational waves and fundamental physics. Beyond astronomy and cosmology, gravitational waves offer opportunities to test fundamental physics in ways previously impossible. The speed of gravitational waves has been measured by comparing arrival times of gravitational wave signals at different detectors and by comparing gravitational wave arrival times with electromagnetic signals from the same event. All measurements confirm that gravitational waves travel at light speed to within better than 1 part in 10 to the 15th, exactly as general relativity predicts. This precise measurement has profound implications. Some alternative theories of gravity predict that gravitational waves should travel at speeds different from light speed, sometimes faster or slower depending on the theory's details. The observations rule out many modified gravity theories, eliminating entire classes of alternatives to general relativity. The fact that gravitational waves and electromagnetic waves arrived within seconds of each other after traveling over 100 million light-years from a neutron star merger places extraordinarily tight constraints on any speed difference, essentially confirming they travel at identical speeds to incredible precision. Gravitational waves also have polarization, directions in which they stretch and squeeze space. General relativity predicts that gravitational waves have two independent polarizations, oriented at 45-degree angles to each other, sometimes called plus and cross polarizations based on their shapes. Alternative gravity theories sometimes predict additional polarizations, including breathing modes, where space expands and contracts uniformly in all directions, or longitudinal modes, where stretching occurs along the wave's direction of travel. Networks of gravitational wave detectors at different locations can determine wave polarization by comparing signals, testing whether additional polarizations beyond general relativity's two exist. So far, all observations are consistent with only the two polarizations predicted by general relativity, though more sensitive measurements might reveal surprises. The strong equivalence principle. General relativity is built on the equivalence principle. Einstein's insight that gravitational mass and inertial mass are identical that freely falling objects follow the same paths regardless of their composition. This principle has been tested with extraordinary precision using torsion balances and lunar laser ranging, confirming that different materials fall at the same rate to better than 1 part in 10 trillion. But the strong equivalence principle goes further, stating that even gravitationally bound objects like neutron stars should fall at the same rate as non-gravitating test masses. Neutron stars have enormous gravitational binding energy, roughly 20% of their rest mass energy, meaning a significant fraction of their mass energy comes from gravitational potential energy rather than matter. Some alternative gravity theories predict that this gravitational energy might cause neutron stars to fall differently than ordinary objects, violating the strong equivalence principle. Observing binary systems with neutron stars and testing whether they fall at the same rate as expected provides tests of the strong equivalence principle in extreme gravity regimes. The triple system, PSR J0337 plus 1715, contains a pulsar in orbit with 2 white dwarfs, providing a natural laboratory for testing gravitational theories. By precisely timing pulses from the pulsar as it orbits through the gravitational fields of the white dwarfs, astronomers can measure whether the pulsar's fall rate differs from expectations. So far, observations confirm the strong equivalence principle to within uncertainties, showing that neutron stars fall just as general relativity predicts despite their extreme gravitational binding energy. This rules out certain alternative gravity theories and confirms general relativity in yet another regime: gravitomagnetism and frame dragging. One of general relativity's more subtle predictions is frame dragging, also called gravitomagnetism because it's mathematically analogous to how moving charges create magnetic fields in electromagnetism. A rotating massive object drags spacetime around with it, causing nearby objects to experience precession of their orbits, even in the absence of other forces. The effect is extremely small for most astronomical objects, but becomes significant near rapidly rotating black holes or neutron stars. NASA's Gravity Probe B satellite, launched in 2004, carried 4 ultra-precise gyroscopes designed to measure frame dragging caused by Earth's rotation. The gyroscopes were essentially perfect spheres of quartz, the most spherical objects ever manufactured, coated with superconducting niobium and floating in liquid helium to eliminate friction. General relativity predicted that Earth's rotation should cause the gyroscope's spin axis to precess by about 39 milliarcseconds per year, a tiny angle roughly equivalent to the width of a human hair seen from across a football field. After years of data collection and analysis to account for various systematic effects and noise sources, Gravity Probe B confirmed frame dragging at the predicted magnitude to within 19% uncertainty. Announced in 2011, this was the first direct measurement of frame dragging, confirming yet another prediction of general relativity that had gone untested for nearly a century. The measurement demonstrated that spacetime near Earth is indeed dragged around by our planet's rotation, though the effect is so small that it has no practical impact on satellites or everyday life. Frame dragging becomes much more significant near rotating black holes, where spacetime is dragged around at significant fractions of light speed. The innermost stable circular orbit around a rotating black hole depends on the black hole's spin, moving closer to the event horizon for black holes spinning in the same direction as the orbit. X-ray observations of matter orbiting black holes can measure the innermost stable orbit's radius, providing estimates of black hole spin. Many observed stellar mass black holes have spins exceeding 90% of the maximum possible spin, indicating they're rotating extremely rapidly and creating powerful frame-dragging effects in their vicinity. Naked singularities and cosmic censorship. General relativity's equations allow solutions where singularities are not hidden behind event horizons, but rather exposed to the external universe, so-called naked singularities. Near a naked singularity, spacetime curvature becomes infinite, yet remains visible to distant observers, potentially allowing observations of regions where general relativity breaks down and quantum gravity becomes important. Roger Penrose, proposed the cosmic censorship conjecture in 1969, suggesting that nature prohibits naked singularities, that all singularities must be clothed behind event horizons and hidden from observation. The conjecture has two forms. Weak cosmic censorship states that singularities cannot form from realistic initial conditions without being hidden behind event horizons, protecting the universe from pathological behaviors near singularities. Strong cosmic censorship states that even inside black holes, observers cannot access regions where physics becomes completely unpredictable, that space-time remains sufficiently well-behaved everywhere except at the singularity itself. Neither version has been rigorously proven mathematically, and some solutions to general relativity's equations do appear to allow naked singularities under specific circumstances. Whether naked singularities can actually exist in nature, or whether some physical mechanism always prevents their formation, remains an open question. Most physicists suspect cosmic censorship is correct, and that naked singularities don't exist. But without a complete proof or a confirmed counterexample, uncertainty remains. If naked singularities did exist, they would provide remarkable opportunities to observe quantum gravity physics directly, but they might also cause severe problems for predictability and causality, potentially allowing information to emerge from regions where physics breaks down. The information paradox. Black holes create a profound puzzle in theoretical physics called the black hole information paradox. Quantum mechanics is fundamentally reversible, meaning if you know a system's quantum state at one time, you can in principle calculate its state at any past or future time. Information is never truly destroyed in quantum mechanics, only transformed and possibly scrambled beyond practical recovery. But black holes seem to violate this principle. When matter falls into a black hole, it disappears behind the event horizon, and from the outside universe's perspective, all detailed information about the matter is lost. The black hole is completely characterized by just three properties: mass, electric charge, and angular momentum. A black hole, formed from compressed gold, has exactly the same external properties as a black hole of equal mass, charge, and spin, formed from compressed iron or hydrogen or antimatter or old encyclopedias. This is sometimes summarized as black holes have no hair, meaning they have no distinguishing features beyond the three conserved quantities. But if black holes evaporate through Hawking radiation, which Stephen Hawking showed should be thermal radiation carrying no information about what fell in, then the information about the matter that formed the black hole seems to disappear from the universe when the black hole evaporates completely. This contradicts quantum mechanics' fundamental principle that information is conserved, creating a paradox that has troubled physicists for nearly 50 years since Hawking's original calculation. Various resolutions have been proposed. Perhaps information is encoded in subtle correlations in the Hawking radiation that Hawking's original calculation missed, allowing information to gradually leak out as the black hole evaporates. Perhaps information is preserved at the event horizon in a holographic form, encoded in two-dimensional structure on the horizon surface, even though the black hole's interior is three-dimensional. Perhaps black holes don't evaporate completely but leave behind remnants that preserve information. Or perhaps information really is destroyed, requiring modification of quantum mechanics' fundamental principles. Recent work in quantum gravity and holography suggests that information probably is preserved and gradually emerges in Hawking radiation through quantum entanglement and subtle correlations, but the detailed mechanism remains unclear. Resolving the information paradox completely requires understanding how quantum mechanics and general relativity fit together at black hole event horizons, bringing us back to the need for a complete theory of quantum gravity. The paradox highlights how much we still don't understand about nature's most fundamental laws, despite a century of progress since Einstein. The holographic principle. The information paradox led to a remarkable idea called the holographic principle, suggesting that all the information contained in a three-dimensional region of space can be encoded on the two-dimensional boundary of that region, much like a hologram encodes three-dimensional images on two-dimensional film. Applied to black holes, the holographic principle suggests that all information about matter that fell into a black hole is somehow encoded on the event horizon's surface, not lost in the interior. The principle arose from studying black hole entropy, a measure of information or disorder. Jacob Bekenstein showed in the 1970s that black holes should have entropy proportional to their event horizon surface area, not their volume, as you might expect. A black hole's entropy equals 1/4 of its event horizon area measured in Planck units, an enormous number even for stellar mass black holes. This suggests that the maximum entropy, and thus maximum information content, of any region of space is determined by the boundary's surface area rather than the interior volume. The holographic principle has profound implications extending beyond black holes. It suggests that our three-dimensional universe might itself be a hologram, that all physics in 3 dimensions might be fully describable by a theory living on a 2-dimensional boundary surface infinitely far away. This sounds like science fiction, but has become a serious area of theoretical physics research through the AD-CFT correspondence, a mathematical relationship between gravity in curved spacetime and quantum field theories without gravity in one fewer dimension. While speculative and far from experimentally confirmed, the holographic principle represents a radical rethinking of how space, information, and physics relate to each other. It suggests that gravity in spacetime might be emergent phenomena, arising from more fundamental quantum information theoretic principles, rather than being fundamental themselves. If true, this would be a revolution in physics comparable to general relativity or quantum mechanics, completely transforming our understanding of reality's basic structure. Implications for philosophy and human understanding. General relativity's insights extend beyond physics into philosophy, profoundly affecting how we think about reality, causality, and existence itself. The realization that space and time are not absolute, fixed arenas where physics happens, but rather dynamic participants in physical processes, represents a fundamental shift in perspective. Newton imagined absolute space and absolute time, existing independently of matter and serving as unchanging backgrounds. Einstein showed this is wrong. Space-time is shaped by and responds to matter and energy. There is no stage separate from the actors, no arena independent of the events occurring within it. This interplay between matter and geometry raises deep questions about causality and determinism. In Newtonian physics, if you know all particles' positions and velocities at one moment, you can, in principle, predict the entire future and retrodict the entire past with perfect accuracy. The universe unfolds like clockwork, deterministic and predictable. General relativity complicates this picture. The presence of horizons, regions beyond which light cannot reach us, means we cannot, even in principle, observe the entire universe's current state. There are regions of spacetime that are forever beyond our causal reach, making perfect prediction impossible, even setting aside quantum uncertainty. Quantum mechanics adds additional indeterminism, fundamentally probabilistic outcomes that cannot be predicted with certainty, even with perfect information. The combination of quantum mechanics and general relativity, still not fully reconciled theoretically, suggests a universe that is neither perfectly deterministic nor completely predictable, one where fundamental randomness and geometric complexity conspire to ensure that perfect knowledge of past and future remains forever beyond reach. This has implications for free will, consciousness, and the nature of time itself. Questions that physics alone cannot fully answer, but to which it provides important constraints. The nature of time. General relativity forces us to reconsider what time actually is. In Newtonian physics and in everyday experience, time seems absolute and universal, flowing at the same rate for everyone, regardless of location or motion. But relativity shows that time is relative, flowing at different rates for different observers, depending on their motion and location in gravitational fields. There is no universal now extending across all of space, no objective present moment shared by all observers. Events that are simultaneous for one observer occur at different times for observers in relative motion. This relativity of simultaneity suggests that past, present, and future might all exist equally, that the flow of time might be an illusion created by our consciousness moving through a four-dimensional space-time block where all moments exist eternally. This view, called eternalism, or the block universe interpretation, suggests that your birth, this moment of reading, and your death all exist equally as events in space-time, with only your consciousness's position determining which you experience as present. The past hasn't ceased to exist, and the future isn't yet to be created. All moments are equally real, arranged in space-time like cities along a highway. Alternatively, presentism maintains that only the present moment truly exists, that past has ceased to exist and future is not yet real. But presentism struggles with relativity's relativity of simultaneity. If only the present exists, who's present? Observers in different states of motion disagree about which events are simultaneous, about what constitutes the present moment. There's no objective universal present in relativity, making it difficult to maintain that only the present is real without privileging some observer's reference frame arbitrarily. These philosophical questions about time's nature remain unresolved, debated by physicists and philosophers alike. General relativity provides the mathematical framework showing how time works, but doesn't tell us what time ultimately is or why we experience it flowing in one direction from past to future. The arrow of time, the asymmetry distinguishing past from future, seems connected to entropy increasing as systems evolve toward greater disorder. But why entropy increases, why the universe started in a low entropy state at the Big Bang, remains mysterious, perhaps requiring understanding of conditions before or beyond the Big Bang itself, the beginning and beyond. General relativity predicts that the universe began in a singularity, a point of infinite density and temperature, where the theory itself breaks down. But what does it mean for the universe to begin? What existed before the Big Bang, if anything? These questions push at the boundaries of physics, and perhaps beyond them into metaphysics. One possibility is that before the Big Bang is a meaningless concept, like asking what's north of the North Pole. If time itself began at the Big Bang, created along with space as part of space-time, then there was no before, no earlier time in which the Big Bang occurred. Time is finite in the past, beginning at the Big Bang rather than extending infinitely backward. This seems unsatisfying, appearing to avoid the question rather than answer it, but might be the correct response if time is indeed part of the physical universe rather than an external container. Alternatively, the Big Bang might not be the absolute beginning, but rather a transition from some earlier state. Quantum cosmology models sometimes suggest the universe could tunnel quantum mechanically from nothing, with space-time and its contents appearing spontaneously from a quantum vacuum. Other models propose that the universe undergoes eternal cycles of expansion and contraction, with each big crunch followed by a new Big Bang. Still others suggest our universe might have budded off from a parent universe, or be one of countless universes in an eternal multiverse where Big Bangs happen constantly, each creating a new universe with potentially different physical laws. These ideas remain highly speculative, largely untestable with current observations or experiments. They push into territory where science blends with philosophy and perhaps metaphysics, where empirical evidence becomes scarce or impossible and theoretical speculation dominates. Yet they represent serious attempts by physicists to understand the deepest questions about existence. Why is there something rather than nothing? Why does the universe exist at all? What determined its initial conditions and physical laws? The future of gravitational physics. General relativity stands as one of humanity's greatest intellectual achievements, a theory of breathtaking elegance and profound implications that has withstood every experimental test for over a century. Yet we know it's incomplete, not the final word on gravity, but rather a stepping stone toward deeper understanding. The quest to understand gravity's ultimate nature continues, driving some of the most ambitious experiments and sophisticated theories in modern physics. The coming decades promise extraordinary advances in gravitational physics, New gravitational wave detectors will observe the universe in ways impossible just years ago, revealing populations of black holes and neutron stars throughout cosmic history. Space-based detectors like LISA will open frequency ranges inaccessible from Earth, observing supermassive black hole mergers and perhaps primordial gravitational waves from the universe's first instance. Pulsar timing arrays will detect gravitational wave backgrounds from countless merging supermassive black holes, adding another layer to our gravitational perception of the cosmos. Ever more precise tests of general relativity will probe the theory's predictions in increasingly extreme regimes. Observations of matter orbiting close to black hole event horizons test spacetime geometry where curvature reaches extraordinary values. Gravitational wave observations of merging black holes probe dynamics where velocities approach light speed and gravitational fields are strongest. Cosmological observations trace gravity's effects across billions of light years and billions of years of cosmic history. Each new observation either confirms general relativity once again or potentially reveals the first hints of deviations pointing toward new physics. The search for quantum gravity continues through multiple approaches. String theory has matured into a sophisticated mathematical framework connecting gravity, quantum mechanics, and particle physics, though experimental confirmation remains elusive. Loop quantum gravity offers an alternative quantization of spacetime itself, potentially eliminating singularities and revealing spacetime's discrete structure at the Planck scale. Other approaches, including causal set theory, asymptotic safety, and emergent gravity, explore different paths toward the same goal of unifying quantum mechanics with general relativity. Perhaps future observations will reveal clues pointing toward the correct quantum gravity theory. Perhaps experiments will detect signatures of quantum spacetime through subtle effects on particle physics or cosmology. Or perhaps theoretical breakthroughs will illuminate connections between approaches, revealing them as different perspectives on the same underlying reality. The path forward remains uncertain, but the goal is clear: understanding how gravity and quantum mechanics fit together at the deepest level. Dark matter and dark energy research. The twin mysteries of dark matter and dark energy represent perhaps the most significant gaps in our understanding of the universe's composition and evolution. Together, they make up 95% of the universe's mass-energy budget. Yet we don't know what either one actually is at the fundamental level. Solving these mysteries will likely require breakthroughs in both observational astronomy and theoretical physics. Dark matter searches continue, with ever more sensitive detectors looking for direct interactions between dark matter particles and ordinary matter. Next-generation experiments with masses measured in tons of ultra-pure detector material, shielded deep underground from cosmic ray backgrounds, will probe parameter space for weakly interacting massive particles with unprecedented sensitivity. If dark matter particles have the properties many theories predict, these experiments should detect them within the next decade or two, finally revealing dark matter's particle identity. If direct detection experiments continue finding nothing, alternative dark matter candidates will receive more attention. Axion searches, using resonant cavities and sophisticated quantum sensors, probe the possibility that dark matter consists of ultralight particles rather than heavy WIMPs. Observations searching for primordial black holes test whether dark matter might be concentrated in compact objects rather than spread uniformly. Each negative result narrows the possibilities, gradually constraining what dark matter could be and pointing toward what it must be. Dark energy remains even more mysterious than dark matter, with fewer concrete proposals for its identity and fewer clear paths toward understanding it. Future supernova surveys, observing thousands of distant stellar explosions, will measure cosmic expansion history with increasing precision, potentially revealing whether dark energy's density changes over time or remains constant. Large-scale structure surveys mapping billions of galaxies will measure how cosmic structures grow over time, sensitive to dark energy's gravitational effects on galaxy clustering. The cosmic microwave background's polarization patterns may encode information about dark energy's properties in the early universe. If dark energy proves to be a cosmological constant, truly constant in density as space expands, we face the cosmological constant problem's profound theoretical challenge. Why does vacuum energy have the tiny value observed rather than the huge value quantum field theory predicts? Solving this problem might require revolutionary new physics, perhaps connected to quantum gravity or to fundamental principles we haven't yet discovered. If dark energy varies over time, we need to identify the field responsible and understand its dynamics and interactions. The cosmic horizon. As the universe continues its accelerating expansion driven by dark energy, the cosmic horizon, the boundary of the observable universe, evolves in interesting ways. Currently, we can observe galaxies up to roughly 46 billion light-years away, the co-moving distance to the cosmic horizon from which light emitted shortly after the Big Bang is just now reaching us. But as time passes, the horizon doesn't simply expand at light speed, as you might expect. Due to accelerating expansion, distant galaxies are receding from us faster and faster. Eventually, galaxies beyond a certain distance, currently around 16 billion light-years in co-moving distance, will be receding faster than light relative to us. Light leaving those galaxies today will never reach us, even given infinite time, because space between us is expanding faster than light can cross it. These galaxies are crossing our cosmic event horizon, disappearing from our potential future observations forever. We can still see light they emitted in the past, light already en route that will continue arriving for billions of years, but any light they emit today or in the future will never reach us. Over the next 100 billion years or so, essentially all galaxies outside our local gravitationally bound group will cross the cosmic event horizon and fade from view. Future astronomers in the far future, assuming civilization survives that long, will observe a vastly emptier universe than we see today. They'll see only the merged remnant of the Milky Way and Andromeda galaxies, along with a few dozen satellite galaxies, surrounded by empty darkness in all directions. The cosmic microwave background will have redshifted to undetectably long wavelengths. All evidence for the Big Bang, cosmic expansion, and the universe beyond our local group will have vanished from observational access. This raises an interesting epistemological question. Future astronomers, without access to evidence we currently have, might draw completely different conclusions about the universe's nature, history, and composition. They might think the universe consists only of their galaxy surrounded by infinite empty space, never suspecting the rich cosmic history and vast universe that actually exists beyond their observational horizon. This suggests we should be humble about our own knowledge. Perhaps we're missing crucial evidence about aspects of reality that exist beyond our current observational horizons, leading us to incomplete or incorrect conclusions about the universe's ultimate nature. Gravitational physics and technology. While much of gravitational physics seems abstract and removed from everyday concerns, history suggests that today's fundamental research often becomes tomorrow's practical technology. Relativity seemed like pure abstract theory when Einstein developed it, yet it's now essential for GPS navigation, telecommunications timing, and numerous other technologies. Gravitational wave detection required developing exquisitely sensitive instruments and sophisticated data analysis techniques that may find applications in other fields. Precision timing and metrology, developed for gravitational wave detectors and pulsar timing arrays, improves timekeeping accuracy beyond what's needed for current applications, but may enable future technologies we haven't imagined. Quantum sensors developed for detecting gravitational waves may have applications in medical imaging, materials testing, or fundamental physics experiments. Data analysis algorithms for extracting weak signals from noise, developed for gravitational wave astronomy, find applications in fields from medical diagnostics to financial analysis to quality control. Understanding strong gravitational fields and extreme space-time curvature, while currently purely academic, might someday enable technologies that seem like science fiction today. If we ever develop the ability to manipulate space-time geometry, the implications would be revolutionary. Creating artificial gravitational fields could enable new forms of propulsion for spacecraft, potentially even approaches to faster-than-light travel through warping spacetime rather than moving through it at high speed. While such technologies remain firmly in the realm of speculation, general relativity's equations don't forbid them in principle, leaving open possibilities for distant future civilizations. More immediately, precise understanding of gravity's effects enables better spacecraft navigation, more accurate satellite orbit predictions, and improved models of Earth's gravitational field, used for studying geology, hydrology, and climate. As space exploration expands and humanity potentially establishes permanent presence beyond Earth, accurate gravitational models become increasingly important for mission planning and safety. Understanding tidal forces helps predict stresses on spacecraft and space stations. Understanding orbital mechanics enables efficient trajectory planning, saving fuel and time, education, and public understanding. One of general relativity's remarkable features is that while its mathematics is forbiddingly complex, its core insights can be explained conceptually to general audiences. The idea that gravity results from space-time curvature rather than a force can be communicated without advanced mathematics through analogies and visualization. This accessibility has made relativity a popular subject for science communication, appearing in countless books, documentaries, and educational materials. Yet public understanding of general relativity often remains superficial, based more on metaphors and analogies than genuine comprehension. The rubber sheet analogy, while useful as an initial visualization, misleads if taken too literally and doesn't capture what space-time curvature actually means mathematically. Popular presentations often emphasize exotic phenomena like black holes and wormholes, while neglecting the theory's more mundane but equally important applications to cosmology, precision measurement, and technology. Improving public understanding of general relativity and gravitational physics more broadly remains an ongoing challenge. The theory requires comfort with abstract thinking and willingness to accept conclusions that contradict everyday intuition. Space and time being relative rather than absolute, simultaneity being observer-dependent, and gravity resulting from geometry rather than force, all require mental flexibility and openness to ideas that seem wrong based on daily experience. Yet this conceptual stretching is part of what makes physics exciting and valuable, training minds to think beyond immediate appearances toward underlying reality. Educational efforts continue seeking better ways to convey relativity's insights without requiring years of mathematical training. Interactive visualizations showing how objects move through curved spacetime help develop intuition. Analogies drawn from everyday experiences provide mental hooks for abstract concepts. Historical narratives showing how Einstein developed his ideas humanize the theory and demonstrate the creative thinking involved in scientific breakthroughs. Each generation of physicists and educators refines approaches to sharing these profound ideas with broader audiences, ensuring that humanity's hard-won understanding of gravity propagates through culture, unification, and the quest for completeness. General relativity describes gravity elegantly and accurately, but it stands somewhat apart from the standard model of particle physics, the quantum field theory describing electromagnetic, weak nuclear, and strong nuclear forces. The standard model and general relativity represent humanity's two greatest achievements in fundamental physics, yet they're based on incompatible mathematical frameworks. Quantum field theory assumes spacetime is a fixed background. General relativity treats spacetime as a dynamic participant. Reconciling these frameworks remains physics' greatest challenge. Beyond the technical challenge of merging the theories mathematically, there's a deeper conceptual question about whether gravity should be unified with other forces or remains fundamentally different. In quantum field theory, forces arise from exchanging particles. Electromagnetism comes from exchanging photons. Weak force from exchanging W and Z bosons. Strong force from exchanging gluons. Should gravity similarly arise from exchanging gravitons, Hypothetical spin-2 particles mediating gravitational interactions? Or is gravity something qualitatively different, geometric rather than quantum mechanical at its core? String theory proposes that all forces, including gravity, arise from vibrations of fundamental strings, potentially unifying all physics in a single framework. But string theory requires extra dimensions and makes few testable predictions accessible to current experiments, leaving it unconfirmed despite decades of development. Loop quantum gravity quantizes spacetime itself without attempting to unify with other forces, accepting that gravity might remain distinct. Other approaches explore different possibilities, each with strengths and weaknesses. Perhaps unification requires revolutionary new concepts not yet imagined, ideas as radical compared to current physics as general relativity was compared to Newton. Perhaps the correct theory is already known, but not yet recognized. Or perhaps complete unification is impossible, that different aspects of reality genuinely require different mathematical frameworks that cannot be reduced to a single theory. Only continued research can reveal which possibility is correct, the wonder of understanding. Stepping back from technical details, general relativity represents something profoundly wonderful about human capability. Starting from simple observations about falling objects and planetary motions, extending through centuries of theoretical and experimental work, humanity developed a mathematical framework describing spacetime's geometry and dynamics. We can now predict how black holes form and merge, how the universe expands and evolves, how time flows differently for moving observers and in gravitational fields. We've tested these predictions across cosmic scales, from millimeters to billions of light years, from microseconds to billions of years, finding agreement everywhere we look. Consider the audacity of Einstein's achievement. Sitting in a patent office with pencil and paper, no sophisticated instruments or laboratories, he reimagined the nature of space and time through pure thought. He followed mathematical logic and physical principles wherever they led, even to conclusions that seemed absurd, trusting that nature is mathematical and comprehensible. His theory made bizarre predictions, that massive objects slow time, that light bends near stars, that space itself can ripple and wave. And every one of those predictions, no matter how strange, has been confirmed by observation. This success is not guaranteed or obvious. There's no reason the universe must be comprehensible to human minds. We evolved to hunt, gather, form social groups, and navigate immediate environments. Abstract mathematics and cosmic physics provide no survival advantage to our ancestors on African savannas. Yet somehow, through cultural evolution and intellectual effort, we developed tools of mathematics and science that let us understand reality far beyond immediate experience. We can comprehend black holes we'll never visit, cosmic expansion we can't directly perceive, space-time curvature our senses never detect. This suggests something profound, either about the universe or about human cognition, or perhaps both. Either the universe is deeply mathematical in nature, following principles that logic and mathematics can capture, or human minds are remarkably good at finding patterns and building models, even in domains far removed from evolutionary context. Likely both are true to some degree. The universe does seem to operate according to mathematical laws, and human intelligence, properly trained and augmented with tools, can discover and comprehend those laws. Looking ahead, general relativity is now over 100 years old, yet it remains vital and relevant, still making predictions being tested and confirmed. No signs of breakdown have appeared despite searching in increasingly extreme regimes, yet we know it's incomplete, certain to be superseded eventually by a more comprehensive theory incorporating quantum effects. Future physicists will look back on general relativity the way we look back on Newtonian gravity. Brilliantly successful within its domain, beautifully elegant, and fundamentally correct as far as it goes, but ultimately an approximation to deeper reality. What will that deeper theory look like? We don't know, but we can be certain it will be mathematically sophisticated, conceptually challenging, and probably quite beautiful. History suggests that successful physical theories have aesthetic qualities, mathematical elegance that physicists recognize even before experimental confirmation. The correct theory of quantum gravity will likely possess similar beauty, unifying concepts that currently seem disparate and revealing simplicity beneath apparent complexity. The journey continues, each generation of physicists building on predecessors' work, gradually expanding the boundaries of human knowledge. We stand on Einstein's shoulders, seeing farther than he could because we have his insights, plus a century of additional observations and theoretical developments. Future generations will stand on our shoulders, possessing understanding we can barely imagine, solving problems that currently seem intractable, observing phenomena not yet predicted. Gravity is far stranger than common sense suggests. It's not a force pulling you down, but rather the curvature of space-time guiding your motion through four-dimensional reality. Mass and energy curve space-time, and that curvature tells objects how to move. Simple in principle, profound in implications, beautiful in its mathematical expression. General relativity revealed this truth, transforming humanity's understanding of space, time, matter, and the cosmos itself. From confirming predictions like Mercury's orbital precession and gravitational lensing, through discovering black holes and gravitational waves, to enabling GPS and testing the universe's expansion, general relativity shapes modern physics and technology. It's been confirmed countless times across a century of increasingly precise observations, yet mysteries remain. Dark matter and dark energy dominate the cosmic inventory but remain unidentified. Quantum gravity remains undiscovered despite decades of effort. The universe's ultimate fate and origin raise questions at the boundary of physics and philosophy. These mysteries ensure that gravitational physics remains an active frontier of human knowledge, drawing brilliant minds to fundamental questions about reality's nature. Every gravitational wave detection, every black hole observation, every precision test of relativistic predictions brings us incrementally closer to deeper understanding. The quest to understand gravity, begun with Newton's insights over 3 centuries ago and revolutionized by Einstein a century ago, continues today with undiminished excitement and promise. You now understand gravity not as a simple force, but as space-time geometry, as intimate connection between mass and space-time curvature, as dynamic interplay shaping cosmic evolution and everyday experience alike. You understand that you're not being pulled toward Earth, but rather following the straightest path through curved space-time, that time itself is relative and flexible, that space can ripple with gravitational waves carrying information across cosmic distances. You've glimpsed the profound strangeness underlying mundane experience, the beautiful mathematical structure beneath physical reality. This understanding is humanity's collective achievement, built over generations through observation, experimentation, mathematical reasoning, and creative insight. It represents the power of human curiosity and intellect to penetrate nature's deepest secrets, to comprehend reality far beyond immediate sensory experience. And it remains unfinished, with profound mysteries still awaiting solution, ensuring that the adventure of understanding gravity continues for generations to come. The universe is curved, space-time is dynamic, gravity is geometry. 3 simple statements encapsulating a century of revolutionary physics, a transformed worldview, and a continuing quest for deeper truth. This is general relativity's gift to humanity. Not just accurate predictions and practical applications, but a fundamentally new way of seeing reality itself. Every moment of your existence is shaped by space-time curvature. Every breath you take, every step you walk, every heartbeat, every thought occurs within the curved geometry created by Earth's mass. You are moving through time at a rate determined by your position in Earth's gravitational field. The atoms in your body, forged in stellar furnaces billions of years ago, reached Earth by following geodesics through curved space-time. The light reaching your eyes traveled along paths bent by the sun's gravity, by Earth's gravity, by the gravity of every massive object between its source and your retina. You are not separate from space-time, but embedded within it, part of it, shaped by it. Your very existence depends on gravitational processes that formed our sun, our planet, the heavy elements in your cells. Your future is constrained by space-time geometry, by horizons you cannot cross, by the arrow of time you cannot reverse. You are a pattern of matter and energy following the geometry of curved four-dimensional space-time. Briefly self-aware, capable of comprehending the principles governing your own existence. That comprehension is perhaps the most remarkable fact of all. Against all odds, despite no evolutionary reason for it, human minds can grasp these abstract truths. We can understand that space-time is curved, even though our senses never directly perceive that curvature. We can accept that time is relative, even though we experience it as absolute. We can follow mathematical arguments to conclusions that contradict every intuition built from everyday experience. And those counterintuitive conclusions turn out to be correct, confirmed by observation again and again. This is the real triumph of general relativity. Not just that it's correct, but that we can understand it at all. A species of upright apes on a small planet, orbiting an ordinary star in an unremarkable galaxy, has figured out the mathematical structure of space-time itself. We've observed black holes a billion light-years away, merging in cataclysms of unimaginable violence. We've measured the universe's age to percent-level precision. We've tested Einstein's century-old equations in regimes he never imagined and found them flawless. We've traced cosmic history from the first fraction of a second after creation to the present moment. And we're not finished. New observations will reveal new phenomena, test theories in new regimes, perhaps finally reveal where general relativity breaks down and points toward deeper physics. New theoretical insights will connect gravity with quantum mechanics, explain dark matter and dark energy, unify all forces in a single framework. New technologies enabled by gravitational physics will transform civilization in ways we cannot predict. The story continues, the adventure of discovery ongoing, each generation adding chapters to humanity's greatest story, the quest to understand the cosmos and our place within it. So, the next time you drop an object and watch it fall, remember, it's not being pulled by a force. It's following the geometry of curved spacetime, the straightest possible path through a universe shaped by mass and energy. That falling object is demonstrating the same principles that govern planets orbiting stars, black holes merging in distant galaxies, and the expansion of the cosmos itself. In that simple, everyday observation lies hidden the profound truth of Einstein's greatest achievement. Gravity is not a force. It's the curvature of space-time itself. And understanding that truth changes everything.